already 4 minutes late, I'm sorry for that. So, welcome to the second day of this workshop on new physics searches with leptons. Now we have the pleasure to have with us Professor Alfredo Galindo-Uribarri, who's going to tell us something about neutrinos and advanced detectors. Thank you very much for coming.
All right. So we're changing gears today. So yesterday I talked about an underground detector that requires the lowest backgrounds possible and the cleanest materials. Today I'm going to be talking about back of two experiments that we are heavily engaged. These are happening at Oak Ridge National Lab. What you see there is an aerial view of the Oscillation Neutron Source. Before we move, yesterday we were at lunchtime. This is my little historical vignette. Several years ago, in 1994, we were members of, together with Alejandro Frank and Arnulfo Cepeda. We had a meeting at what is called the Hotel de Cortés. This is by the Alameda Central. And I actually came early to the meeting. And next door, what had happened was there was an earthquake in 1985, and they moved the desk and some of the items of the President of Mexico, Benito Juarez, and they moved them to another palace that is just next door. And while I was waiting, I walked to that place, and that was a temporary location of the Recinto de Juarez. And I found this, that at the desk, at the back of the desk, there was a yes. There you go. Okay. That at the back of the desk, there was his books. And when I was looking at it, I felt to be quite curious. And I noticed that one of the books, it said something like experimental physics. It was in Spanish. It said Física Experimental. And it looked quite modern. And if some of the old timers, you might remember that in that area, it was an area where they sell a lot of old books, right? It was the libros usados on that region. So I said, oh, you gotta be kidding me. I have to, I'm gonna protest, I'm gonna go and talk with the curator. And I said, look, they probably stopped with any books just to make it look that it was full. And the guy said he had about 50 keys. And the guy said, no, that was Benito Juarez's book. So he came over, he opened a barrier, he took his keys, he opened the book, and he said, do you want to see it? And he gave the book. So I was so, my hands were all sweating, I started cleaning my hands and so on. And turns out that indeed, there is this book. It was it's called Física Experimental, it's from 1790. It was Teodoro de Almeida, was a Portuguese scholar. And I was really quite happy to see that because, apparently he did teach physics while he was in Oaxaca. Alfonso Mondragon knows the story very well of Benito Juarez, but this is something that, for example, in the U.S., I don't know if you have Benjamin Franklin and so on. So this is something that I find it very interesting that one of the most famous presidents of Mexico had some interest in physics. I wish that some of the more recent presidents would have the same type of interest. Anyways, so with that in mind, let me go to the outline. So essentially, this time around, the program that I talked about yesterday is funded by Nuclear Physics, Department of Energy, and today these are essentially more of high energy physics. Again, Oak Ridge was not a traditional high energy physics. It is only very recently, for some of the reasons I'm going to be mentioning that they have become interested on some of our facilities. So I'll talk about Prospect Coherent, and I won't have time, but there are new initiatives more associated with potential use of computational sciences, and there's a lot of things of machine learning are some of these new buzzwords, and people are looking at potential uses of quantum information within the field of high energy physics. Just again a reminder, you saw this yesterday. This is just to illustrate that from the physics division, about 1 mile in this direction is the spallation neutron source, and about 1 mile in this direction is the high flux isotope reactor. So what we have started is a broad research in nuclear particle and astrophysics. The emphasis is in weak interactions and fundamental interactions, and we're essentially concentrated in neutrino oscillation, neutrino properties, and the search for neutrino with double beta decay. So this, as the same way as nuclear physics has its long-range plan, similarly there are the so-called P5 reports, and this fits quite well within these plans. We learn a lot about for 100 years or so, we have been learning about the nucleus properties by throwing things to the nucleus and looking at the response, or waiting that the nucleus emits something and we learn from its response. And along the years, people have developed specific tools, specific accelerators, and specific detection systems to deal with several of these probes. I have particular interest on these probes, which include, of course, the emission of the 2 electrons, polarization within the context of nuclear physics, particle gamma correlations, and more recently, tritium beams. Tritium can be important in nuclear structure studies, in particularly in the 2 neutron transfer reactions that can give information about matrix elements that are required for the double beta decay. And of course, more recently, using the probe of the neutrinos in order to get additional information. To do this work, we need sources. So we have reactors, we have accelerators, there are different processes, and we need a suite of detection systems, and that's what we'll be talking about. We do have, somebody made the joke that instead of the spallation neutron source, we should call it the spallation neutrino source. Indeed, 20 years ago, we had an effort to try, there was a project that was called Borderland, and a collaboration that was called Condor, and the idea was that we wanted to build a big bunker of about 7 stories high at the end of the spallation neutron source. At that time, the building was being constructed, the accelerator was being constructed, and pretty much DOE did not want any distraction. The spallation neutron source main users are, this is funded by JET, another branch of DOE, which is called Basic Energy Sciences, and the community was very large, about 3,000 users from condensed matter. So basically, we did not succeed, and it took about 20 years for us to convince them that indeed this type of research is relevant and has a lot of impact. The reasons why this is an important source is the most intense neutron source. It's a pulse neutron source. It's 1 GeV of protons. There's a LINAC that is shooting protons in this direction. There's an accumulator ring, and then this is the region of interaction. The power is quite large. It's 1.4 megawatts of beam power, and more important for the type of information I'm going to give is we're in the process of building JET a second target station. This time around, we're discussing with them about space for neutrino detectors, So we caught the attention of this community, and this is going to give us additional opportunities to build neutrino detectors specifically associated with the Spallation Neutron Source. So we do have a very good opportunity there with the second target station. The high flux reactor that we have is an 85 megawatt research reactor. You can see here the core as it's being lifted. You see the Cherenkov radiation. The core is very, very compact and is highly enriched uranium fuel at the level of 93%. The origin of the neutrinos and the mechanisms are quite different, and the spectra is shown in here. In the case of the reactor, essentially what we have is a neutron on fissioning uranium-235, then you have uranium-236 momentarily, then you have an asymmetric split, and then you have a chain of fission fragments that this one decays in beta decays into this one, lanthanum, cerium, and so on. And on average, you have 6 neutrinos that are being produced on the process of the fission process. But you have a very large variety of fission fragments, and each of them, they have the very specific nuclear structure properties. So what you see at the end is the cumulative sum of something of the order of about 800 fission fragments, and that are beta decaying, and they have a corresponding neutrino in the process of doing that. The energy range here, you see the scale is the upper scale is up to about 8 MeV. So these are very, very intense flux, continuous flux. So in the case of the reactors, we don't have and I'll come back to that, we don't have the timing structure that is very, very important in order to see these very weak signal events. So what yesterday, Stella? Okay. Stella gave a very nice overview of coherent. Here, essentially, we are looking for to characterize very precisely the antineutrino spectra, and there has been some observation of an excess on around 5 MeV neutrinos that is being called the shoulder, or is being called the bump. And this is, I'll come back later on, but the point I'm trying to make here is that the reactors produce a huge flux of neutrinos at low energy, few MeV, but no timing structure. In the case of the Spallation neutron source, the source of neutrinos is different. It's called the pion decay at rest neutrino source, and Stella yesterday explained that indeed, again, the scale is relatively low energy. This is up to about 50 MeV, but as it was explained yesterday, this energy range is perfect for things like coherent neutrino scattering. So again, characteristics are large flux, not as large as the reactor, a few tens of MeV, and sharply pulsed timing, which is very, very important for background rejection, and this is what had impact in terms of our work for the coherent neutrino scattering. In addition to that, we have other resources that are useful for the high energy physics community, in particular in computing facilities that include currently the world's fastest supercomputer called Summit. Within the physics division, we have our own cluster, large space for high bay area where we can assemble detectors and so on, and space for visitors, etc., etc. Okay, so yesterday, again, I talked about the differences in a very, very different type of environment. Here, we want, in the case of neutrinos, the whole beta decay, we want to go down, we want to go to a mine, we want the purest materials possible, and we're also interested, of course, in the ways of assaying and and determining the purity of those materials, but we are dealing with different types of backgrounds. Today I'm going to be talking about Prospect, hyper-coherent at the Oscillation neutron source, and here we are above surface. The challenges are very, very different. We have huge backgrounds coming out from the reactors, and there are very specific challenges. Yesterday, Stella mentioned about did a very nice job in terms of pointing out that indeed there's a worldwide search. There's a lot of interest in this topic of sevens, and I should point out that all of these experiments are reactor-based. So it's only the Oscillation neutron source experimental coherent that we're using to accelerate. Again, I'll go very quickly about through this. It is not surprising. So yes, it was predicted 40 years ago, the process, and it was observed, and kind of people would expect to have sevens. So this is predicted in the standard model, and the idea again is to try to use multiple detector technologies and try to get this n-squared dependence of the cross-section. So the coherent elastic scattering initial final states, of course, as it was pointed out yesterday, they must be identical. Again, the process depends on the scattering of the neutrino and the signal given by the nuclear recoil, and this is where the challenge comes. Again, the calculations are well understood, the differential cross sections and the nuclear recoil energy. We are trying to look for this n-square dependence. The cross sections by neutrino standards are huge, so that should facilitate seeing the process above other processes that occur with neutrino scattering. But nucleons must recoil in phase. The coherent process is coherent, say, up to about 50 MeV, so we're right in the right range, but we have very low energy nuclear recoil, and the experimental signature is less than 50 keV deposit from the nuclear recoil, and this is a process that is very, very difficult. The people that have worked in nuclear physics in the past, they have studied some of these processes of the interaction of radiation with matter. In fact, one of the world's experts was this fellow here, and in terms of studying what happens when you have radiation interacting in matter. So was proposed in '74. Why is being measured until now? Part of it has to do with a lot of developments on dark matter detectors, and this over the last decade, and of course the push is very similar, that it's coherent to try to detect signals on the order of a few tens of keV recoils. And the other element is that we have stronger neutrino sources, and now we have access to close proximity. So as it was mentioned yesterday, in September of last year, we published in Science the first observation of neutrino of coherent of sevens of this process, and indeed it was a 14.1 kilogram cesium iodide. It is indeed a handheld neutrino detector, and this is the signal in terms of time and energy in a little 3D model. But the point I'm trying to make here is that it took 16 months of data. So even with all these advantages that we have, this was a 6.7 sigma type of signal. The detection is not trivial. Okay, where do we do these experiments? We have coined the term the Neutrino Valley. Turns out that we explore different sectors at different positions within the Oscillation neutron source, trying to look for a quiet sector. And one of the main problems that we have is the backgrounds coming out from fast neutrons. And this is something that's very difficult to completely chill. You see here the beam is going up this way. It hits the target in here, and you have of the order of about 18 different beam lines. One of the there are a couple of beam lines that physics division is doing. There are several experiments that are also going from different sectors. There's a very important experiment on fundamental symmetries, and there's a neutron PDM experiment that is going to take place in here. The Neutrino Valley is about 20 meters, 20 to 30 meters, depending on this position along the corridor. It is on the sub-basement, and there is a lot of, it's ideal in the sense that there is a lot of steel, gravel, and concrete, and essentially we have of the order of 10 meters water equivalent above, and all of this helps to get the signals. This is a layout, and just to illustrate that the cesium iodide experiment was done in this location, and there are several experiments that are going on. For example, a liquid argon experiment has been taking data for quite a bit of time. The analysis is in progress. We'll soon have results coming out from this guy. There is a prototype here of about 185 sodium iodide detectors. There are several of these from a project on Dick Cheney that made a lot of large sodium iodide detectors. So literally there are tons of this material. We want to make the germanium array, and there is a study going on what is called the neutrino means, that is neutrino-induced neutrons on materials such as lead and iron. And for doing this, actually we are between the two collaborations, Prospect and Coherent. I'll talk a little bit later on Prospect. Prospect is lending Coherent some of the liquid scintillator in order to improve the detection of this process that again is important to quantify some of these cross sections. So you saw yesterday some of the plots. Essentially our value is somewhere here on the cesium and the iodide, and there is some deviation from the pure n-square dependence having to do with the neutrons, or through the nuclear form factors. What is the future for Coherent? Where are we aiming to? Again, n-square dependence. We need to have other technologies to prove that is indeed following this chain. But we are aiming to go to precision measurements. 7 by itself, okay, we see it is nice, but I think there are many other things. Yesterday they were touched about non-standard interactions, nuclear physics, form factors, and axial currents, and also there is considerable interest within the community of studying supernovas about cross-sections. Cross-sections are also an important aspect of some of this work. So essentially we want to go to large statistics, accurate measurements of the electron spectra, and that's where we are aiming. The detector technologies that have been used with reactors, they include organic materials. Of course, some of the problems with these ones are that yes, they have exquisite low thresholds, but then you need the mass. Then you need to make a large amounts of this, or you need exposure. You need to be waiting there for a long period of time. In the case of the decay at rest, basically all of these are being considered. We recently had we invited an external committee, some of you might recognize several of these guys, that they came over, and this is a little like the, again, shameless advertisement. This is like a movie review. So just to quote, the SNS provides a source of decay at rest neutrinos that is unique in the world in its intensity and time structure. Of course, they praise the detection of coherent neutrino scattering from a nucleus, and also they praise the fact that on the P5 recommendation, the idea is not necessarily just to go and do Dune physics. Dune is all that community, a lot of them are going that way, and I think it is important to have a program at all scales and from mid and small scales. I like these ones because I can see them happening and my students can see them from the beginning to the end, and it's a compelling and unique scientific program at SNS, and it could lead into new physics in a cost-effective way. A few finer details about the process at Duke University, Phil Barbeau and collaborators. Again, it is very important to study the very low energy response of some of these detectors, so for example scintillators, and he has made a setup, but what they do is they do a nuclear reaction that produce monoenergetic neutrons, and the sample or the material that is being investigated is placed as a target, but it's an active target. So essentially this might be coupled either, well, several electronics. If it's a scintillator, it would be coupled to a small photomultiplier tube. And then what you are looking at is the scattering. You place a series of neutron detectors. This is a very open room where you don't have a lot of the problems associated with neutrons being backscattered from different things. And the kinematics itself, having the coincidence between the target and the series of detectors, essentially determines the energies that you are looking in terms of the light response. So the idea is to try to measure the so-called quenching factors and to study nonlinearities of the materials. The idea of using neutrons is quite nice, because instead of using charged particles that at very low energies, essentially the only thing that you are sampling is the very surface. In the case of the neutrons, basically you are sampling the bulk of the material. So this is crucial for some of the interpretation, and many times it is one of the main areas of uncertainty of the results, because you have to do corrections as a function of energy of the responses of different materials, and there is discrepancies on the literature about what is the behavior at these very low energies. So again, this is a full program of trying to investigate some of the materials that could be used for doing this type of work. I mentioned already the fact, the process that the cross sections for these neutrino-induced neutrons that can give us that can be a background for the process of coherent. We have a program in terms of trying to determine that cross section, because the predictions, they can differ by as much as 30%. Again, immediate goal for coherent. So test the proportionality of the cross section to the neutron number squared. We're implementing with our colleagues from Chicago 10 kilogram germanium detector. This has been funded. We will move to a 2-ton sodium iodide detector, and 2 new projects, and we have a very large degree of certainty that this will move ahead, is to build a 1-ton liquid argon detector. And we want to go for we need to calibrate the neutrino flux and do a better job. And to do that, there is a proposal, and that will be led locally to do a 1.3 ton of heavy water detector. So this is kind of the price tag, and all the signals from DOE is that yes, we will be going ahead with the construction of these 2. Switching gears, I want to talk a little bit about searches for sterile neutrinos. This is another project I'm deeply involved, and this is precision oscillation and spectrum experiment. This is happening at the reactor. And this cartoon basically illustrates the location, the relative location of the detector. Roughly speaking, we're talking about 4 tons of lithium-6 loaded liquid scintillator. This is based on some, the basis is the commercial one is LG 309, and that provides us pulse shape discrimination. And this is to illustrate the size of the core of Hyper. So as you see this, here is the reactor core. We can go as close as 7 meters. And then the idea of building this was that this could be, that we could use air cast and that we could move 75,000 pounds of detector in a range between 7 and 12 meters. So we could change the distance from the reactor core. Some of the commercial reactors that have been used, Diabase, Reno, Neos, etc. This is roughly the size of the reactor core. So this is really a beautiful point-like source of neutrinos. Again, motivations are the so-called 6% flux deficit as compared with this baseline. I'll talk a little bit more about that in a minute. And then to do a search for short baseline oscillations and address the hypothesis of the possibilities of having stellar neutrinos. We also are interested on measuring very carefully the spectral deviations, the so-called bump. And in addition to that, we want to characterize what is antineutrino spectra produced when you have a highly enriched uranium material. Some of these other research reactors that I mentioned, they don't stop. What happens is that they, as they are producing energy, the material is transmuting. You are breathing plutonium, and the plutonium has a different antineutrino spectrum. So what we want is also to characterize it very, very careful what is this neutrino associated with it. This is just to illustrate something I mentioned before. In fact, the fission fragments for uranium are being used for radioactive ion beam facilities, essentially. What the radioactive ion beam facilities, some of them, what they do is they fission an actinide, and then you have the production of many neutron-rich nuclei, and you choose one, you ionize it, and then you use it to do a reaction. Here, essentially, we're just interested on the corresponding antineutrino that they produce. Many years ago, there was a John Hardy, Bjorn Johnson, Hansen. They wrote a paper that was called Essential Decay of Pandemonium. Pandemonium was a fictitious nucleus, and essentially what they wanted to demonstrate was the complexity that happens when you have the beta decay and you have many weak transitions and you have very high level densities, how you can, by studying them, you don't study the beta decay. The beta decay is basically a continuum. What you study is the gammas coming out from the various levels that are being populated. And the point was that it's not giving you the full picture of all the beta strength. So these are very difficult to detect with detectors that have low efficiency. And there has been a trend in the nuclear physics community, and this is complementary to the antineutrino spectra. Again, this is coming out from the nuclear physics community, where things like this. This is about 1 ton of sodium iodide detector, and essentially a sample from those fission fragments. Somewhat you transport them, you put them in the middle, you have a silicon detector, you detect the beta in coincidence with it, and then you use the full array as a calorimeter. You are no longer interested on the individual transitions, but what you are is you're interested on the sum of them, and then you can introduce all the information that is available. You can do the convolution, and there is a very strong effort to try to study especially those that are contributing in the antineutrino spectra on the high energy end. So beta decays of fission products are being revisited with this type of technology. This is needed in order to establish the true decay schemes and the antineutrino energy spectra. MTAS, this is our detector. This is the world's largest and first modular total absorption spectrometer measuring full decay patterns, including beta neutron energies. And about 80 cases have been measured. About 15 they have been verified, modified, and this is also important for reactor operation. There's something I will have time to deal with, which is the decay heat. For reactor physics, it's important to know exactly what is the real decay heat in order to operate on the safe regime and push and get as much of the reactor as you can. But the important thing is that there is a change in the reactor antineutrino anomaly estimate from 95% or so to about 97%. Point I'm trying to make is that that baseline that we're talking about the anomaly and the 6% is kind of shortening because of we had incomplete nuclear physics information. Many of this information is coming out from huge data sets, and the point is, if something is remain, of course, then there might be some interesting physics behind. It is also interesting to point out, however, that the shoulder, the bump, has increased by doing some of these corrections. So again, the shoulder doesn't seem to be disappearing. So we, Oak Ridge, got involved very early in this process since late 2012. We have a big advantage of being the host institution, so we can be involved on many different aspects of it. Even the logo was designed by one of my students. The laboratory, Oak Ridge, has a very strong tradition in neutron sciences, and along the years there have been about 13 reactors that have been deployed at Oak Ridge, and Hyper is the last one, the newest one. Of course, this was in 1965, and the reason that it had a very compact core had to do with that Glenn Seaborg was pushing for a very high flux, trying to get n squared, trying to get additional farther away transmutations into the actinides, and because he was interested on this search for superheavies. In fact, now it's paying off. As you might have heard recently, there are 4 new elements. One of the new elements was named after the state of Tennessee. It's Tennessee, and that came out because the material is being produced here at Hyper in terms of the newer targets like curium, berkelium, and so on, that are allowing to push that type of search. Right. Okay, so this is the bay that's they're extracting the material. Prospect is about 7 meters from there, and this is just simply how we do have a big advantage that in order to do this type of studies, you have to collaborate with the people that are operating the reactors. The people that operate the reactors do not give you necessarily the information. Some of this information obviously is classified, so we have a big advantage of working directly with the reactor physicists and know exactly what are the activities that are going on that will give us some issues with respect to the factors. So this is just to concentrate the flux in the central portion of it. Again, a little bit of details. That's 93% enriched, However, 99% of the neutrinos are coming from the uranium-235. The core, inner cores, outer core, and the way that we run is by cycles. Again, we have a big advantage with some of the experiments that are being done in commercial reactors. They don't stop. So here we run for 25 days. The whole core is being removed, is placed on a next door in order to cool, and then we have another cycle of around a month where, we have about the period of a month where we can measure the background. So measuring the background is almost as important as measuring the signal. So this is a very nice controlled way of trying to do these measurements. Again, a close-up of the core. The fuel is in these plates, 171 fuel plates in the central part of the core, and 369 fuel plates. This has been working out for, right now it's 452 cycles, and there hasn't been any failure. It is all the reactors in the world are going to go from high enriched to low enrichment, all of them. However, we think that this one will be the very last one to move. So we think we still have a window of opportunity of about 15 years where we can study and characterize very well this response. Here, again, backgrounds is a big issue. We don't have the luxury of having a lot of overburden. Essentially, this is neutrino detection at the surface. That's basically what we have. We do have the limitation of the floor weight. We're limited by how much weight, and the studies of this, you can imagine, you cannot just simply bring your stuff to a reactor and place it and say, oh, we have to put 75,000 pounds of material in here. And also, by the way, we want to put a wall against the reactor wall of lead shielding. And so the process took a lot of negotiations with and a lot of studies, seismic studies, etc., in order to establish the detector. I'm going to go through a series of mostly pictures to give you an idea of the scale of the project. This is the access door, so essentially a truck can come from the other side, and we have a very nice access, and this is the wall against where we put the reactor. As local group, we did a lot of work in terms of fully characterizing the background. This is a prototype. I think I coined the term the coffin of the collaboration. Didn't like that. I think once in Halloween, I think I put a T-shirt that was a skeleton. I laid myself on that of the collaboration protest, so no coffin. This is an array that was built by my students. Essentially what we did is we have 8 sodium iodide detectors, 8 fast neutron detectors, a helium-3 neutron detector, a helium-3 moderated, and the idea was to have basically the same electronics as we are using for the full array, and scan in 3 dimensions on the region that we were going to do the measurements in order to fully characterize. And with this information, we feed the information through the people that were doing some of the simulations, and then the design was an iteration of how much shielding we should do and where we should be putting the shielding in order to fully characterize the neutron background coming out from the reactor, the gamma background coming out from the reactor, and we did also some cosmic ray tests. More recently, turns out that some of these facilities, they use superconducting magnets for the program of condensed matter. And some of these superconducting magnets, they can go up to about 11 Teslas. And the problem, of course, when you're using photomultiplier tubes is that you have to be careful that some of the magnetic field might be affecting the response of your detectors. So all the time, in space and in time, we need to monitor what are the activities going on within the reactor. Just to give you a little bit of an illustration, there's a cold neutron source, a cold neutron beamline that goes in this direction. There's another beamline, and this is one floor below. And what we are doing is trying to do a measure and determine where are the hot spots that could potentially produce a symmetric signal within the area. This is with high resolution. This is germanium detectors, and essentially what you have is reactor on, reactor off, reactor off. Of course, most of the stuff is coming out from radiation from the walls, etc., etc. Reactor on, there's a lot of captured reactions that go to high energy like ATL. So again, it is important to know exactly what are your sources in order to do mitigation, background mitigation strategies for this type of experiments. As a byproduct of these studies, we had this interesting behavior. This is a large sodium iodide detector. These are the rates. This is when the reactor on is happening, and then the reactor shuts down, and these are different energy beams with the reactor off. But I just draw your attention to these little blips, and it turns out that these little blips correspond to the time, exact time when the sample was removed. There's a little blip in here, and the inner field was removed, the outer field was removed. Again, nothing to do with the neutrinos, but this is, by studying the backgrounds, this can be an interesting, nice application to know what's happening on the other side of the wall in terms of activities of the reactor. The way our detector was designed is a matrix. It's 154 segments of 11 by 14. It's kind of a big aquarium where we have a double-ended photomultiplier readout. We digitize all the signals, so there's tons of data that is coming out from this thing. And the key was also to develop a specific liquid scintillator that is doped with about 0.1% of lithium-6. Lithium-6 is a strategic material, so we have to account for this material. And also we added a tiny amount of trace of actinium-227, and this is essentially to have a relative response. Or you cannot, you always have some issues on the tolerances when you're building something. So all the various cells, they are not identical. They are not exactly the same. So a good way to do it is you basically float this actinide. The actinide on the chain produces a couple of alphas. They are very well localized, and what you're having is the relative efficiency of all the segments, and that you can make the corrections adequate for that. The principle of detection is, again, the so-called inverse beta decay, and this really has the time structure in the lithium-6. That's the case about 40 microseconds later, that you have tritium and alpha being decayed. This topology has been very important in order to do the cuts to suppress the background. Again, the typical spectrum, you're talking of anti-neutrino spectra of mean energy of the order of 3.6 MeV. So these are low energies. In preparation with it, the detector was assembled at Yale University. We had many meetings. We collaborated. The whole collaboration sent people to help assembling. This is a workshop, analysis workshop. Several of these are my students. So the collaboration has worked out very well, and everybody has had a chance to really get the hands-on work on the liquid scintillator, on the production of the reflectors at the Illinois Institute, and at Yale, the photomultiplier testing and so on. This is in December of last year. This aquarium is basically being lifted. Just some of the specs we started running since March 6th of this year. So we're taking data. Again, I won't go to many of these details. Perhaps I just to highlight that we claim we have the best. We have the best energy resolution of about 4.5%, and this is important. Again, to give you a little bit of an idea of the scale, these are activities of the physics division. This is a big ISO tank where we mix the liquid scintillator, and yeah, it was kind of a challenge to get this thing in. Again, some of my students we received from Brookhaven the liquid scintillator. We kept it on the nitrogen gas for a period of time. We were very careful in terms of weighting the masses, etc., etc. There is a lot of processes in terms of quality control, quality assurance on the optical processes of the liquid scintillators. Liquid scintillators are a pain because they can be very sensitive to various environmental conditions, and we did sampling of these. These are optical, these are UV spectra of the individual samples that went in, and the red thick line is the sample once they were mixed. So we were very happy that was, in terms of the quality control, that everything that was going in pretty much had the same optical characteristics as what it was mixed. This one is the one corresponding to the actinide that had that was of course 1 out of 28 barrels. This is at the physics division. Again, just to give you an idea of the scale, we were very concerned about the temperature conditions of the liquid scintillator, so we had to wrap it, and here it is arriving to the heifer. We're about, as I mentioned before, about 1 mile. We brought this thing in. There had to be a lot of the equipment sometimes is done ad hoc. So they have to be inspected and so on. This is a laser pulsar that is used as well for calibration. This is a mock-up. It turns out that we had to shape the floor of the reactor. And again, a lot of paperwork to do that, because of course you come with these guys and to say, oh, we want to, your floor is bumpy. We want to shape the floor, and sure. So this cost a fortune to get the machines and make this thing even in order to get the detector in. Of course, as physicists, we always try to get to push the limits. So what is the maximum amount of liquid scintillator that we could put in, and what's the biggest size that we can go with, and we did that. This is coming in from the outside, and that was fun because this air cast started wobbling at the beginning, so everybody was worried that we were going to hit some wall of the reactor. The pulse shape discrimination, again, this liquid scintillator allows you to distinguish between heavy particles and light particles, neutrons and gammas, and you can define very well the region of the IBPs by looking at the shapes of the digitized signal. I mentioned this about using actinium-227 that in the process of decaying produces these 2 alphas that are very well localized, and that gives you a quantification of the relative volume of the liquid scintillator. We have the cells, they are slightly shifted by about 5 degrees in such a way that you leave some space here, and that space is very important because we can put sources with this mechanism at the end, and we have several sources in order to measure the light output for the different cells. So we declare Prospect complete. This year it was really assembled in a record time, and that is a full Prospect against the wall of the reactor. You see part of the lead wall that is chilling Of course, you can use the approach of shielding completely the whole array or shielding the source. And of course, shielding the source is the one that puts less weight into the reactor. So we saw, important thing is about 3 hours after you turn this thing on, you see neutrinos. So we're very, very happy about that, and with all the pods that we have, we are actually seeing neutrinos. We're seeing neutrinos of the order of 750 neutrinos a day. And this is some preliminary data as a function of baseline, and what you expect is, of course, the 1/r² behavior from the different cells. So again, we're very happy. Both projects, Coherent and Prospect, we were very happy that we started to get high visibility in terms of publications. I mentioned Science. We very recently submitted the first paper from Prospect. This is being refereed at TRL, and it's on their archive. And there is nuclear instrumentation papers associated with the response of the detector. A little bit about the collaboration. We are of the order of about 16 institutions for Prospect, and Coherent is a similar number, about 16, and we are the only institution that is common to both collaborations. I guess I should count University of Tennessee as well, because I also have, I'm also part of University of Tennessee. So Prospect and Coherent, I want to emphasize the fact we had 3 theses. The first 3 theses of the Prospect project came out actually from my students, so I brag a lot about that. And also there have been a couple of theses that came out from people from the University of Chicago, from Duke, on the first results coming out from Coherent. So this is a great place to train young scientists. I flash some of the people that have been involved. This particular case, they have been students and postdocs, several of them from Latin America. There's guys from Sonora, UTEP, Universidad del Estado de Mexico, and so on. That along the years, either I bring a lot of students from Mexico. Normally, I have worked more with the nuclear physics community, so along the years, I probably had about 35 or so every summer. And there are about 28 more from the collaboration institutions, and similarly with the students you recognize on that?
Yeah.
Okay. And there are students and postdocs that work in Coherent, again, very large numbers. And in fact, this guy, I believe, has won the APS award of the best thesis. And this just to give you an idea that it's not only these guys. Putting something on a national lab involves, these are about 80 people that they had to do something related with installing the detector. So there's a very large infrastructure behind that is needed in order to, even that these are smallish scale projects, there's certainly a lot of fun to deal with many of these guys. So immediate goals for Prospect is to do a reactor model-independent search for sterile neutrinos at the EV scale. We have the segmentation in order to do that. If we see some oscillations, we should see them. To measure and understand the uranium-235 reactor at the neutrino spectra, we started taking data. We detect neutrinos at surface from a reactor. We have done the first oscillation analysis with the data. Of course, we go through a process of blinding the data, releasing the data, and so on. We are working very strongly on the spectrum analysis in progress, that is in progress. And in summary, we do have world-class resources, HYPER, the Spallation Neutron Source, and the so-called leadership computing facility. We have a strong group with deep expertise in projects, detectors, and experimental techniques. We have a unique, cost-effective scientific program with 2 shallow depth experiments. The collaboration involves more than 130 scientists from 30 institutions. I was a little bit surprised about these numbers, but more than 75 students and postdocs have been involved. We certainly have a strong support nowadays from the management. Prospect was successfully completed and is taking data in this mode of reactor on, reactor off. We have done the first observation of sevens. We're publishing in high-profile publications, and we are being approached by other collaborations. Halo, for example, is one. Halftime is another one, and so on. And we're discussing how to proceed from here. So we have an effective research plan to build on that success. However, just about 10 days ago, this came out. So Neutrino 4 is reporting the first observation on effect on oscillations. This was Cerebro and others that was put on the archive, and they have a measurement of this. The claim is at the level of 3 sigma. We are skeptical. It's poorly written, the paper, but this guy has a lot of weight. This is the person that claimed about a decade ago some of the results on the neutron lifetime that were low, and now everybody seems to be converging to his values. The paper, I invite you to read it, is interesting in the sense that it quotes us, and it says something like, "Oh, Prospect should confirm our results," or maybe not. It's along those lines. Of course, if we confirm them, they are going to be claiming they were first to observe. Bottom line is this. We'll see. This might confuse things because it's difficult now to prove a result that they resulted from. The most difficult thing that you can do is to prove. You have to do a significantly better experiment than these guys in order to prove that they are wrong. Otherwise, you're confusing the field. The field is going to be investing a lot of it, and if through these results, and of course, there's a lot of technicolor here. If you remove the red line, not quite sure that you see this type of oscillation, but still, this is getting this is sending a lot of it's putting a lot of pressure on the collaboration and of course in the competition as well. So with that, thank you.
Well, we have plenty of time for questions.
What's the corresponding mixing window?
I think the data is here, and it points is 7 eV, 7.2 eV, which is a large one, and the sine square is 0.35, if I can read it correctly. So it's we are working on the exclusion zone, and there's a joint meeting at the American Physical Society and the Japanese Physical Society in Hawaii from about 5 days or so, and yes, everybody's working concerned about what we're going recently. So it's interesting. If there are oscillations, of course, the results are huge. The implications are enormous. To see something like that, if it's really some oscillation. So again, it's a very. They knew that the other people were working on it. They cannot do much better, and the paper is full of a description of what they would do better if they had blah 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 blah. So we had some ham, we had some eggs, we had an omelette. Well, they are talking about improvements for the future. So I guess this is important in the sense that this is focusing a lot of communities into the similar problem. There are people like Hannah Hayes in Los Alamos, for example, working on magnetic corrections on the beta decay. So this is nice in the sense that people from various communities are refining the measurements. They are forcing to, they should reconcile what's happening from the nuclear physics, what's happening from the experimental design, and in the process of doing that, we're learning the challenges of doing this neutrino detection and so on. So I think it's very exciting times that we're living, at least on the neutrino side of things.
Is it a damage what?
That is where I think it's 0.35. I can send you the requirements. So it's yeah. I don't want to make sentences.
More questions, please.
Yeah. You see, in this radioactive beam facility, you mentioned that you produce neutron-rich nuclei, and then you have anti-neutrino, a continuous spectrum of anti-neutrino. I have a question, and I will motivate my question.
Okay.
The question is, do you have also proton-rich unstable nuclei in that case?
Yes.
The reason I'm asking this is because if you have proton-rich, you have, apart from the possibility of beta plus, what is interesting is that you have instability by electron capture. And with electron capture, you have a monochromatic neutrino beam. The monochromatic neutrino beam, the advantages of that and the possibilities, particularly if you boost the beam in that case, and you have a neutrino beam with definite energy. In fact, this was discussed, was the PhD of Catalina Espinosa, and it's published in JCAP. And you see, this was essentially the motivation to have you see, at higher energies, but you can do it also at low energies at that case, and then look all the effects associated with the search of neutrino oscillations at low energies, and in particular for steroids, in this case, with neutrinos instead of antineutrinos. You understand why the question is relevant? You could have proton range.
Absolutely. So in this radioactive ion beam facilities, in our case, our cyclotron was basically here to do fission fragments or very light nuclei because of the energies of the proton. So we had something of the order of 50 MeV, and our strength was on the fission fragment spectrum. Other types of facilities that are the so-called ISO facilities, for example, Prime is one, and CERN is another one, the ISO facility. Essentially what they do is they produce by spallation. So in that particular case, yes, you do have both sides, proton-rich, neutron-rich production.
Okay.
There has been discussion as well to do experiments with source, right? There was the famous one called SOX they were supposed to put a very strong source in Borexino that was being produced in Russia, and that was cancelled. That didn't go. So people have thought about producing a very, very strong source and try to use some of the existing detectors, or to do kind of decay in flights, where these are accelerator-based neutrino beams as well.
Maybe it was then is an accelerator. But you see, in that case you don't need to have energy resolution in the detector.
Correct.
You can put in the detector an effort for the other component.
Correct.
And you know, it is like a high energy physics experiment. You know the energy just from the source, not constructing the energy in the detector.
Right. So I do believe that there's going to be quite a bit of development once we, right now people are this has the focus of many of very large community of people. And of course in neutrino physics things happen in steps of many decades, right? We're making progress on decade long. And I think this is accelerating a little bit of the interest in terms of neutrino physics. And I can see more of development, technical developments along the lines of what you're saying.
Yeah, I think
That would be it.
The original reference is in the thesis of Catalina,
Okay.
this idea.
More questions? Doubts?
Yes.
What is the time scale for the argon detector in procurement?
We, okay. So we're running the smaller, relatively smaller version, and this has been running for months right now. So we think that we will have, we'll be releasing soon results. This other project, we talked directly with DOE. We had a review about a month ago, and we are giving it priority. We're going to make it work, and most likely the proposal will be delivered in the early next year. So 2019, we will talk with them. And this is at the scale where it doesn't go above certain thresholds that DOE has. So it's very likely that it will move very quickly. So I can see this happening in the next year, 2 years max.
That's cool. And the small one that has already
The small one has already data, and I'm told that Los Alamos, Bill Lewis and company, they're also trying to do TPC, liquid argon TPC. This is based on Captain, and I think they're going to get into the game with the argon measurement. In that particular case, they go for a much larger volume, and this is TPC. Not clear how well that will work. And they have about 30 times less flux than what we have on this.
Okay. Are there any further questions? No?
Would it be possible to move the detector to explore different baselines?
So yes. So the principle was designed in such a way that we would have 3 movements. Not quite easy because you really have to disassemble a lot of the shielding first. Then you bring this system to elected, and then you move it. So the original plan was to move it to the center one. But if these oscillations are happening here, most likely it will stay on the location right now. Yeah. So yeah, we might change a little bit the strategy. The other plan that we had in the initial stages was to have a differential measurement, to do a prospect times 10 outside the building. So in that particular case, they're very precise. If you have exactly the same technology and you measure the differential measurement between kind of total distance and building longish distance of maybe 25 meters. So that would be outside where you get much more change. So that, again, the problem is so this project is cost altogether about $5 million. So this is DOE funding and the Hysins private foundation. They gave us the rest.
Okay. So I don't see right now any urgent further question. So we thank Alfredo again for this. So now the coffee break was planned to be at 11. Now we have like 28 minutes to just play around to see whether some coffee or some cookies are already prepared there as yesterday. Let's see whether we find something. Thank you, Chair.
Okay, thanks for the very kind introduction and thanks for having me here. So it's a really nice workshop. I'm going to talk about a lot of this, and I'm trying to only be some part of the talk very basic. And what I'm going to discuss here is of course based on many papers of mine. Some of which are trying together with Neutron or Solomon. And before I get started, just a disclaimer. Don't jump at me. I'm very sparse with citations or references here because I already put some material in the slides. So if there's certain citation missing, that doesn't mean that I don't think this paper is useful. I just have not time to look at it in our space. So of course we are all high energy physicists, so this is a cartoon of different energies which are relevant to these talks. So of course we start at very low energies. Before it's actually the cosmological framework is the scale of nucleosynthesis. This is the very first elements of our universe were formed. Then in particle physics there's of course another very important scale which is the electroweak scale, which is roughly the scale class of weaks, or the W bosons. And we will learn more about this from the talk. We know that somehow in the early universe there must have been some minor genesis, because you want to deep information which in a certain way produce an empty universe which has to be in all this meta asymmetry. And then there's another scale which is not a scale we should really know, but this more like an inferred scale, which is a scale of gratification. And finally there's of course the scale of gravity, Planck scale, which is 10 to 18, 10 to 19. What we in a certain way know very well, of course, not to an arbitrary position that we understand quite well these days, is these physics at these scales up to 100 GeV, because this has been tested in gliders and so on and so forth. So there we have a very good understanding. But everything here, this is really subject to major speculation. So we don't really know if our world has a unique conditions. There are reasons to believe this, but we don't really know. Gratification, maybe it is there. And neutrinos in a certain way provide us with a very nice window into these high energies. This has to do with something which is known as seesaw mechanism and other things, which I'm going to have you here. And the basic upshot of all this is that neutrinos can be used to tell us more about all these high energy scales, which we can make educated guesses on, but really don't know. And at least neutrinos provide some means to test these ideas. Good. So there will be two parts of this talk, but they will not precisely, I'm not going to discuss all of this in this lecture and all of this in the second lecture. There will be different splitting, depending on how things go. I will briefly tell you why I think that neutrinos also motivate an extension of the standard model. I will tell you the seesaw, which has been of course used in previous talks, so we'll just review it. We'll briefly talk to some extent about neutrinos and quantification. We have already heard yesterday this very nice seminar by the under that quantification anyway has problems. This motivates me then to switch gears a little bit and do some discuss a little bit string model building. And I also will give some additional information on speed validation, things which have been discussed yesterday already in the show. And then there will be another part where we discuss neutrinos, but we will see how time goes. Good. So what is the overall framework of all this? Okay, we are all physicists. We all know that in nature there are certain forces which we observe. So one force is of course gravity, which keeps me here down at the ground. And this has been known, of course, very long. This is somehow how physics started. It's new to avoid these things. We also know, of course, that there is magnetism and electricity, which we know from Maxwell's theory. So these things are all very historic things that we know for ages. We also know for quite a long time that there are weak interactions which are relevant in all these decays of nuclei and so on and so forth. And what the standard model does, the standard model particle physics does, is that it unifies these things in one common language. This is all based or described by a simple gauge theory with the gauge group SU2 left cause U1 hypercharge, and these symmetries are there but get spontaneously broken at a scale of the order 100 G, which is called the electronic scale. We also know that, of course, there are these strong interactions which are mediated by the gluons and which keep the quarks together, protons and neutrons of our world. And these three forces or gauge interactions which are listed here, they comprise the star. And what you're seeing a certain way here in this picture is already that there is some unification which has already happened in the past. So in the very beginning, people didn't really understand that gravity is one thing which describes both the motion of planets and us being stuck here on the ground. So unified in gravity. And here these things have been unified in the standard model to this extent. The idea of grand unification is that all these gauge interactions that you observe have a common origin, a common description in the so-called grand unified theory. And the most naive guess on what the relevant scale here, the analog of the electronic scale here, will be 10 to 16 GeV for reasons which I'm going to reference. Of course, this still leaves some questions open because you see we have now maybe a unified description of all these phenomena and in addition gravity. And if you are more ambitious, of course, you would wish to unify these things as well. Of course, there's one characteristic scale in this game, which is the scale, the Planck scale, which is just 1 over the square root of Newton's constant. And this evaluates to something of the order of 2G. Okay, and of course the question will be how neutrinos fit in this. Just to repeat, all our understanding of forces of course has one universal principle, which is that you have local and continuous symmetries, and all forces which we observe so far can be traced back to some government. Continuous symmetry, like other coordinate transformations, or some albedo 1, or some AC3, or some AC3. Good. I'm also going to talk about the early universe later. They use this cartoon to motivate certain things, and then these scales, which I just mentioned, will be relevant. Good. There are many things which we know, and which we have, of course, discussed at great length in the previous talks. We know, for instance, that neutrinos oscillate. But what it essentially means is that if you produce a neutrino in a certain flavor here, you may detect it in a different flavor. And we see even that this transition probability has this oscillation shape, so that's why these things are called neutrino oscillations. We have also now a rather clear picture on the relevant neutrino oscillation parameters. So we have mass eigenstates. We don't know what the absolute mass is, we don't know what the lowest of these masses will be. It can be 0 at the present time standard. What we do know, however, is the mass splitting, so these differences between mass squares. We know that there's a larger one, smaller one, which are called atmospheric or solar, because this is the first experiment in which these quantities have been measured. And we know how these neutrinos are composed. But we don't know at the moment very well is the mass ordering. We know there's a slight preference for this so-called normal ordering. We don't precisely know this. And depending on these mixing angles are also preferred mixing angles are also slightly different. We know, of course, the parameter resonance and the MSW effect, which also help us to understand the neutrino properties better, but you see that all these neutrino properties are of course highly relevant. You see that there are some conversion of neutrinos. The energies of these experiments have been discussed at length, and there are certain parameterizations which give us all these mixing angles. So this is essentially some slight generalization of a 3x3 rotation matrix with one more physical parameter which enters here in form of phase. This is called CP phase. And in various different experiments, we put somehow pinned down the relevant parameters here. As already mentioned, there are like 2 large mixing angles and 1 semi-small mixing angle. So we don't really know them to a super high precision, but rather precise. We have some amazing accuracy, and to a very first approximation to these different notations, which are also probed in 3 different experiments. What we don't know very precisely, and this one is of course the CP phase. There are certain hints that suggest that CP violation is favored in the lepton sector, but this is not high precision at this point. The other things which have been discussed, so this is all still very basic. We know, of course, neutrinos are produced in beta decay. Beta decay is a standard model process which gets mediated by the charge W boson, and this is a timeline diagram. What we don't know whether or not it exists, and this is indeed a very fundamental question, is whether neutrinos are their own antiparticles. If there are, then there is a chance that we will see a return neutrino with double beta decay. This has also been discussed at length. And I think it's really highly important because you see, whenever you give a very basic introductions to particle physics of the standard model, you can do everything and write down everything in the corrosion, but what you cannot do at the moment is to write down the neutrino mass term because you don't know what it is. There are still 2 options. It can be either the effective neutrino mass operator, or it can be just the mass term. And when we give very basic particle physics lectures, we never really know which one it is. 2 options. Everything else in the standard model you can just write down. This is a nice certain coffee cup where you write down the whole portion of the standard model on a coffee cup. The only thing which you don't know is missing on this coffee cup is the neutrino mass. Of course, we all hope that in some near future we will know have a better certain coffee cup where this mass operator is also. We have seen that, of course, you can parameterize the transition amplitude in terms of some effective neutrino mass matrix. And even if neutrinos are Majorana, you may not observe them in a certain mass range because there can be translations which come and involve the so-called Majorana phases which do not show up in the oscillation amplitude. But in this expression here is this phi1 and phi2 phase. There's of course also other attempts to measure neutrino mass from kinematics simply because neutrino acquires a mass, the end point of the spectrum will be shifted. But this is of course a tough measurement, and I plan to talk more about this at the end of the second lecture. But what I want to now is of course to just give you a more theoretical motivation for the importance of neutrinos, where they come into play, and why the structure of the standard model itself, in a certain way, already strongly suggests the existence of a Brighton and therefore of neutrino mass. We know, of course, in the standard model that we have different particles. So, for instance, there is a left-handed quark doublet. So, the notion doublet means it's a doublet. There's 2 components under something, and the something here is the SU2 left gauge symmetry. So these transform as doublets. That means there is an upper and a lower component. And the fact that these are quarks simply means that they transform as a triplet under SU3 colors. That means these guys have colors. And these are the 6 members of the left gauge doublet. There are other doublets, which are the lepton doublets, and this is where the neutrino shows up. So the lepton doublet, the left-handed lepton doublet, comprises both a left-handed electron and a so-called left-handed neutrino. And the fact that they are doublets simply means they transform non-trivially under this SU to the left, meaning that they couple to the W bosons as to the right-handed quarks do not couple to the right-handed, to the left-handed W, the W bosons. So they are triples under SU2 with the color, but singles under SU2 left, and there are two different types of them, the up and down type quarks. There's three generations of each, but this is what you have in the standard model. And finally, one thing which is also exists in the standard model is that there are the right-handed electron types, because there's a muon and a tau part. And as you see, from this description, is that there's a big asymmetry between left and right, because left are doublets, there's an SU2 left, but no SU2 right. Of course, people have, from the early days on, they have came up with a left-right symmetric version of this standard model, where you combine these singles to a doublet and a new SU2 right hypothetical gauge symmetry. So if you do that, things become more symmetric. You know, these guys are all of a sudden more symmetric. To an SU2 right symmetry, which connects kappa and lower components of those, but if at the very moment when you do that, of course you have to do the same thing to the leptons, and you end up having a right-handed neutrino. So this has been studied for a long time. This means you can make the standard model more symmetric at the expense of using this new degree of freedom. At the very moment you have this degree of freedom, we have discussed it already yesterday at the end of the talk. And you can of course write down a mass term for these things, because there's no symmetry within the standard model alone which predicts this mass term. So you can write down a mass term for objects, and another term which is of course also consistent with all the symmetries of the standard model. It's just a Yukawa coupling which connects these right neutrinos to the left-handed element. And it's just the analogon of the usual Yukawa terms that you have anyway for all other charged terms. If you entertain this possibility, you will somehow an extended mass matrix, which is the so-called seesaw mass matrix, which has the off-theoretical components, just the usual Dirac mass terms, and the lower or right component will just the mass term. And any undergrad student who has attended some linear algebra lectures will of course know that here in this 2x2 matrix you have two characteristic quantities which are the determinant and the trace. The determinant just gives you the square of the Dirac mass term, whereas the trace is expected to also just the right-handed mass term. And from this we can immediately write down the mass eigenvalues. Immediately the mass eigenvalues we have simple relations. The product is the square of the Dirac mass term. The sum is the sum of the mass eigenvalues. It's just the Majorana mass term of the right-hand mass term m. And this gives us eigenvalues which have in the limit in which the mass term of the right-hand neutrino is larger than the Dirac mass term, the shape of m Dirac square over mass, and just the second mass term, which is just the right-hand mass of the right-hand neutrino. And now, in order to fit with this formula observation, in order to obtain masses of the order of 1 electron volt, which is suggested by the atmospheric mass square difference, you want to have some mass of the order 10 to the 4 G. Of course, this is all very naive in the sense that in order to arrive at that, we have to plug in here something of order 1 for these power couplings, something which is true for the top quark in the standard model. So if you look at the other ones, it's true for the top quark and the other values. Any case, so this gives you seesaw-suppressed neutrino masses, which have suppressed masses. So you can explain the fact that neutrinos are so much lighter than all other things, but just diagonal some approach that hide a large mass can go. And in this case, in a certain way, to some value approximation, the Night states are more or less the active neutrinos, those guys which couple to the W and Z bosons, whereas the heavy guys are more or less the neutrinos who do not have any standard propagation interactions and are sometimes sterile, but one has to be very careful with this terminology because it has been used and abused in several ways. The upshot of our hypothesis is, of course, that you need some largish scale M in order to have a very simple explanation of the smallness of the neutrino masses. And this scale M is of course important because it's very large, and therefore you can argue that this allows us to at least indirectly show physics at very high scale. And I just told you that the very naive scale here will be 10 to the 14 G. So in some sense you can of course now hope the neutrino masses allow you to probe physics at a scale as large as 10 to the 14 G. So this is one of the most important features of the consequences of the smallness of neutrino masses. Good. This is something which I'm not really going to discuss here. What one would say is that one can get this neutrino mass operator by integrating out the right neutrino. This means you arrive at an effective high-dimensional operator in the standard model, which contains the lepton couplets in the X field and a coefficient which has mass dimension -1. So this is a so-called non-randomizable operator. But what is sort of amazing is that if you just look at the structure of the standard model itself and you ask, what are the higher dimensional operators which you can write down? Then the unique answer is that at dimension 5 there's just one operator, this is this one, and this is the operator which is whatever for each other is. So the first operator which you get in this game is the neutrino mass operator. You can write it in this diagrammatic form. It has just these legs, but these legs really comes from integrating out these right-handed neutrinos, which essentially means that in the propagators of these guys you can neglect the kinetic force. And this will be slightly, I will come back to this a bit later. And string models, we will see that here you have predictions on the number of right-handed neutrinos, which is in the standard model completely unknown because it's just an H signal. You can have one of them, 100 of them, 10,000 of them, and the standard model doesn't tell you anything about this. But of course, if you do a string model, you can start counting these. And you get an idea how many neutrinos are there. And this will also affect the coefficient of this operator. Good. Another trick, and this is just a side remark, or a technical side remark, in order, of course, to play all these games of unification, you in a certain way want to allow for transitions between quarks and leptons. So you want to put them in a larger scheme, have a unified description of all these guys. But of course this doesn't really work if these fields have different transformation behavior under Lorentz group. So that is, if you have left chiral and right chiral states at the same time. But okay, the only thing which prevents us from unifying these different multiplets is our convention that we say we have right-handed quarks. This is just a convention. This is simply a convention which stems from the fact that, let's say, the material here built up in this blackboard, is made of quarks, left-handed quarks and right-handed quarks. These are the quarks which enter our surroundings. But at the fundamental level, we can describe, as well decide that we want to describe everything in terms of left chiral degrees of freedom. We could do that, but then we would say, the guys sitting here in this blackboard, these are left chiral antiquarks. This is all what we need to do, is a change of convention, but this allows us to describe everything in terms of left chiral deferments at the level of the standard model. And the only thing is that then these guys will transform as antiquarks. Also the hypercharge, of course, gets inverted. And this is the standard trick which you want to do in grand unification, because once you have this, you can in a certain way start putting these multiplets into larger schemes. and thus allow for transitions between quarks and leptons. And you want to do that in order to unify all gauge interactions, 3 gauge interactions in the standard model, into some larger group. And now I'm going to discuss somehow the role of neutrinos in these games of unification. So one way to go even beyond this left-right symmetric version, which I just sketched before, is to go to the so-called partisan model, where you in a certain way no longer want to separate quarks from leptons. You can do that by making just lepton number the false color. That's the wording chosen by partisan in their paper. So you can just embed these things into a 4-dimensional representation. You just say this false color is lepton, and then you would have 4 2-lets under this partisan group, which now SU4 now contains a standard SU3 of the standard model, with some more, something else, which makes it 4-dimensional. You switch to SU4 representation. And you can do that for the right-handed guys as well. And this tells you that by doing that you arrive at something which looks like SU4 cross SU2 left cross SU2 right. Now from group theory you of course also know that SU4 is almost the same as SO6 and SU2 cross SU2 is almost the same as SO4. So what really is written here is an SO6 cross SO4. Already hints at SO10. Another way to do the unification is going along the route pioneered by Georgia and Glashow. So who put the standard model left-handed quarks, the right-handed uptype quark, and the charged lepton into this 10-dimensional representation of SU5. So this is an antisymmetric SU5 matrix. And there's really a miracle going on because this fits into this representation even more. There's a unique U1 SU5, and this precisely gives you the right height and charges for these guys. And the remaining representations that fit into 5 bar. Sorry, I forgot the 5 bar. It should be 5 bar. Group theoretically, it's true that both SU5 and partisan are subgroups of SO10. Even more, the group theoretical intersection between SU5 and the partisan group, which are the very first groups which have been proposed for unification, is precisely the standard model. So the group theoretical intersection of these 2 candidates of a unified description is SO10. So this fits in SO10, and this of course strengthens the role of SO10 in this group. Another thing which you might want to consider doing is to use supersymmetry in this way. So here, in this discussion, the primary motivation for adding supersymmetry is that if you add supersymmetry at the TV scalar to this description, then some miracle happens, namely the gauge couplings unify. What that means is, if you use ordinary quantum field theory to extrapolate this E known and measured gauge coupling of the standard model. So this would be the gauge coupling of the strong interactions. This would be the G2 gauge interactions of the W bosons, and this would be G1 in the standard model, which is the coupling of the P boson for symmetry breaking. So these all unify at one point at the high scale. And this is something which does not happen in the standard model alone, but it happens automatically if you add supersymmetry. And among many things, it allows you to unify these gauge interactions and also gives you a new scale. And this new scale which emerges here is something of the order of 3 times 10 to the 16. So you have now a new scheme. You can entertain a picture of a unified description of all gauge interactions that you know of. And the scheme comes with a new scale, but this scale is of course far, far, far beyond the reach of our current providers. So that means that there are some indirect hints that suggest that the standard model really is a remnant of some larger gauge group, SU5 or SU10. And the fact that we see some very different forces in our experiments at low energies is not that these forces are different, they are always the same in some sense, but it's just quantum effects, which once you add them will make the strong force strong, the other forces weaker. The fact that we see some strong SU3 has nothing to do with SU3 being different from the others at a fundamental level. It's just that there are well-controlled, well-understood quantum effects which make this happen.
May I make a comment?
Yeah, sure.
In order to find the three lines in one point, the only thing you need is to break one of them in the trajectory. For example, if you have left-right symmetric models in a different region, then you can have also.
Sure. Once you add additional degrees of
You have
freedom
to
at some
add,
scale,
you have to change the
Sure.
gauge group. Yes, of course.
Sure. You have in a certain way three
Left-right
lines.
symmetric.
And
yeah.
you, sure, I mean, this is just a statement. If you add additional parameters, you have three lines. In a
What I
standard
mean
model, they
What
don't-
I mean is that this is not proof of supersymmetry.
it's not a proof, absolutely not. It's just somehow the accident is that in SUSY you have, of course, a scale. You want to somehow relate supersymmetry to the electroweak scale. So you only have one scale. And then you add the degrees of freedom which you anyway have, and then this happens. It's absolutely true that if you add new ingredients like right model, some additional degrees of freedom, and in addition adjust the scale, you can always make this work. There are tons of papers on this. The only thing is what is worrisome about this somewhat is that you have to adjust the scale. But it's true that for a given set of additional degrees of freedom, it's quite likely that you find a scale that works. Sometimes it doesn't work because the scale will come numerically out we want, but there are many known examples where you can have gauge unification with all this percentage. Of course, it's not that simple because if you start playing this game, also the scale where these couplings meet will change. This scale where these couplings meet can be tested indirectly with proton decay. What that means is if you want to have a scenario in which these scales meet at 10 to the 10 GeV, you may be doomed because the proton will decay too quick. And the standard thing here, bottom line here, is that the scale of current unification or of gauge coupling unification is suspiciously close to the scale which we wanted to have for our need CISO mechanism. So that of course suggests that these things are not completely unrelated. Again, it's no proof, but this is somehow the scales which we get out, and we could have been very unlucky that we get 10 to the 8 GeV here and 10 to the 29 GeV there, but it's not. They are actually rather close. And of course there are attempts to explain this. And these attempts are most prominently done in the context of SO10, which is something which contains both Pandemonium and SO5. And the one, maybe most important feature of SO10 is that it allows you to combine the quarks and leptons, all quarks and leptons of one single generation in one simple irreducible representation, which is the scalar representation of SO10. There's just one representation which contains up quark, down quark, electron, everything you need to make protons and neutrons and the material of black hole and neutrino. Everything is contained in one single 16 bit. They can be, of course, depicted or visualized in various different ways as somehow effective. 2 to the 5, 2 to the 4 is as 16. Can be some plus and minus signs with a constraint that the number of minus signs is even. And if you do that, then you can arrange one independently of the standard model in some simple scheme. I think, I mean, this gauge coupling unification is a nice thing, but really this is the thing which is the most striking indirect evidence for crack unification. But rather than writing down all these freaky standard model representations on 3,2 with charge minus 1,6 and then unto 3 with comma 1 with charge 2 or 3, you have just one thing. This explains the one full generation of the standard model 1. And once you have 3 of them, you heard this yesterday in this nice talk, then they have the full standard model better content. This kind of unification to many doesn't look like excellent. That's something fundamental to it. Problems start, we already heard about this yesterday, is when we really construct models of this type. Of course, you know that we also have discovered Higgs. Higgs is essential to break the electroweak symmetry. But what turns out to be a really good feature for these quarks and leptons, that you have these complete microgrids, is somehow something which is bad for the Higgs section. Because there's no way we can just introduce one electron to be coupled and 2 of them in an SO model. Rather, the smallest representation, which contains the Higgs doublets, is a template of SO. Now this simply means you get 2 more Higgs triplets, 2 more color charge particles. Additional, and this is a very important thing, grand unification, the fact that we arrange these meta multiplets in these large representations, of course, will allow now for transitions between quarks and leptons. But as soon as you think about it, you will see that this is something which is, of course, very dangerous, because it will tell you that ultimately the proton may not be stable. And in fact, as we have heard yesterday, the very first, or some of the very first successful neutrino experiments actually were motivated by proton decay experiments. So what that means is you have simply additionally you have couplings between quarks and leptons, like this one, which gets mediated by extra gauge bosons, which are gauge bosons of SU10 or SU5, but not gauge bosons of the standard model. There will be these transitions. You can draw these Feynman diagrams, and they will eventually give rise, if you run this image for the proton or neutron, you can get proton decay. So this is roughly how it looks like. You have a proton here, but then these extra gauge bosons will mediate transitions from this pair of 2 up quarks into an anti-down and a positron. So look what you have here. This is of course just an ion. And this tells you that there will be, if this whole story is true, then there might be something like a proton decay process. People found this of course intriguing for many decades. They have been looking at this for many dedicated experiments, and maybe as a comment now, because you made this comment that this NDE stands for nuclear decay experiment. This is true, and the people were actually very optimistic to discover proton decay in these experiments, because at that scale, at that time, the most promising models of grand unification were non-supersymmetric. With non-supersymmetric models, as we know by now, gauge couplings do not unify, but at that time, the gauge coupling of the strong connections was not known that well. It was just taken such that the couplings unify. And they do unify at a scale of 10 to the 15 GeV if you are happy to adjust the G3 coupling. Now the proton lifetime is of course inversely proportional to the mass of these Higgs bosons with a power 4. And if you put in here something like 10 to the 15 GeV, then you get the proton lifetime of approximately 10 to the 30 years or something. And this is actually something which could have been really tested in the superconductor experiment. Unfortunately, before they really were finished with the experiment, people thought, no, it has to be switched. supersymmetric unification, that is this 2 times 10 to the 16 GeV. And you see this has, of course, a drastic this is just a factor, a huge factor, that such that in the end you get something here like 10 to the 34, 5 years, which is too long for observed. Anyway, so this is also just tells you that you have to be actually very careful in playing these games by adding states such that the gauge structure is unified. This can work, but it can also lead to tension as existing proton decay lifetime constraints. So we know that, okay, it depends on the decay mode, but we know it's more than 10 to the 33 years or so. So this is what you get. And you see it sensitively depends on the scale of the mass of the gauge process. Good. Good. What you then can do is, and we have seen this yesterday in the talk, and I'm not going to discuss it in too greater detail. You can start building gut models, which are certainly just analoga of the standard electroweak standard models, except that you have a different gauge symmetry and a different peak sector. You need all sorts of crazy representations, like 45 bits or even larger representation to do the symmetry breaking. You can write down models, and you find, of course, there are certain things which do not seem right. One of the things is that if you look at the Yukawa couplings of the standard model, the fact that the quarks and leptons are unified in one simple representation, the 16-bit, suggests or tells you that at tree level and at the high scale, there's only one Yukawa coupling. So this is the only renormalizable coupling which you can write down. And this just tells you that the Yukawa matrices for up types, down types, and charged leptons and also for neutrinos should coincide. This is, of course, something which seems very bad if you look at it from this perspective. If you do the running of these couplings, it actually doesn't look that bad anymore because it's something which works out rather well for the heavy generations. That is, if you run the top mass and the bottom mass and the tau mass and the indices m down, then for some appropriate function beta, you redo this unification over if you want them. But these relations are terribly wrong for the later generations. So this is something which is, of course, a problem. Now, you can, of course, try to fix this by adding higher dimension operators here and there. But then you have a game which is half-only arbitrary. So you can write down couplings of this type. If you do that, you can also have like nice seesaw mechanisms, or have a seesaw mechanism, and the seesaw scale as the gut scale or Planck scale, or Planck scale, which is actually a nice fit. The only problem with that is that it becomes very, very arbitrary because you add things by hand, and you add this with this coefficient and this with that coefficient, and it could be all true, but it's very hard to test. If you look into the literature of current unification in even more detail, then people typically want to have something like a 126 bar. This has to do with their desire to generate the neutrino masses for this term. This is one motivation. A bigger motivation comes from the fact that this allows you to retain some supernova parity in the sector, which is something that you really sort of want to have if you really have supersymmetry. In any case, you can do that. You retain the standard seesaw picture, so this is something which you can easily fit into this unified model. But if you do this in the context of four-dimensional unification models, then somehow you have to live with all these ugly high-dimensional constellations. But of course, in the old days, people were really excited about this because in a certain way they were suggesting that these relations allow them to test their models of quantification. Problems with that is that the 126 splits are not available exchange theory. So now, of course, you may say, okay, then who cares? I believe in string theory, and that's all. Then string theory is wrong, these models are right. The real problem with this attitude is that there are other problems to this scheme which can simply not be solved with 4 dimensions. And the most drastic of these problems is the doublet-triplet splitting problem. This is the problem which I just mentioned, that there are the smallest representation, which contains the X, also contains some color triplets. And among the many things which these guys do is that they give you additional source for proton decay. And the important thing about this diagram is that this is a so-called dimension 5 operator. So this is less harmless than the proton decay operator which I just discussed previously. So the superserimatric model you can write down with this coupling, this effective coupling here, and you get a diagram like this. This gives you a different decay mode. You get proton decay to a K plus and an anti-neutrino. But the bad news about all this is that this diagram is no longer suppressed by 2 powers of the mass of the nucleator, but only 1 power. And this makes it very hard to hide this diagram. In fact, if you look at papers by Stuart Larvey, who after all writes the review for particle data group about quantification, here's paper that the mass of this guy has to exceed the Planck scale in order to be consistent with this oscillation. So that's a really tough problem, so in a certain way we really don't want these states. So yeah, what you typically get, if you really work on the model, there's of course a lot of stuff going on, you have to know what these couplings are for. But in the really explicit models where people have done all their homework, you get actually very tough constraints. So what we have seen is, of course, we have certain mutations which interfere to unification, which seem to be gauge coupling unification. And what is even more important, the structure of matter. Again, you can unify all this mass, which makes up one generation of model matter. All this mass just is contained in 1/16. And you explain all the quantum numbers, all hypercharge, everything is explained just from this book theory. And the real problem is that if you apply this logic, which is so beautiful here, to the Higgs vector, you really run into problems. Good. Of course, now you might say, then I have a more complicated sector, there are some bimopolar switching mechanisms, some missing partner mechanisms, you know what? People have looked into these mechanisms and always found that at a given point they do not. So this is when you might of course wonder, so maybe they were just not clever enough and didn't construct their model in such a very nice, compelling way that everything works out smoothly. But actually one can prove that they will never work. One can prove analytically that you will always have some problem. You will always have to sweep some operators which you don't like under the rug or something of this kind. This is simply because if you had a mechanism which really takes care of this double triplet splitting, you would have a symmetry which explains why these doublets are light and doesn't require these triplets. So you would need a symmetry reason which tells you that these are light. And it turns out that one can actually pin down what these symmetries can be. So that one can constrain the possible symmetries, which would be just a job. I will very briefly go through that. I'm not going to discuss this in detail because it is very technical. But the upshot is that if you use certain very basic ingredients, which are certainly there in string modeling, but which you also want to have field theory, namely that all the symmetries are somehow at some level anomaly free, that all anomalies get cancelled. And if you don't want to mock up gauge coupling unification, meaning that you don't introduce very crazy green Schwarz axiom in this context, then it turns out that there's only one symmetry which doesn't change. So of course we also want to have neutrino masses in this game, we want to have fermion masses. If we have only from these requirements, under the assumption that you have SO10 unification, you find that there's only precisely one symmetry which can do the job. If you relax this a little bit to SU5 relation, then you find that 5 different possibilities. I'm not going to discuss this in detail unless you ask me. There are some well-known papers that show that the only way to kill the Higgs bilinear at the MSSN is to use R symmetries. And you can just then use anomaly constraints to constrain these symmetries. This is all very basic elementary mathematics. But you find that there's simply one unique symmetry. You know that matter charges have to be bound under the C form. It's an R-symmetry, which is a symmetry which does not compute with supersymmetry. So this is more technical detail for the experts. And you can work about the charges there. Good. So you know what the symmetry is. You have actually not too many possibilities what the symmetry could be, which allows you to understand why the Higgs is light. But now you can of course say, okay, the next step is I just construct a model which has this symmetry. So that model which has this symmetry. Okay, so I'm going to just mention this here. And the basic point is you cannot have any asymmetry in a four-dimensional model of grand unification without having additional exotic, dangerous, massless light states. So you can prove that you can never have such asymmetries from four-dimensional models of grand unification. And the basic argument is that if you have the standard mechanism of gut symmetry and SU5, then you have to assign this field some asymmetry. But the fact that parts of these multiplets get eaten by the extra gauge boson leaves you with certain states which have, because you want to have an unbroken asymmetry, are charge 0. But they can never get a mass term. Simply, these are real representations, but the superpotential is R charge 2. You can never write a mass charge. You can now, of course, add extra 24 bits of this type, but then you can show that there will be additional representations of these types, which are massless. You will always end up with some very exotic extra states, which stay massless until supersymmetry is proven. And you can then convince yourself that this happens for any finite number of 24 planets. This will happen for any group which contains a CO file, so this will always happen. And the only way out here is, of course, to have an infinite number of 24 planets. This is something which we are not really familiar with. But if you look at extra dimensions, then you know, of course, there is the so-called Klein tower, which has an infinite number of states. And in extra dimensions, this no-go theorem doesn't apply, simply because there's the U-pole infinitely many 24 bits. Notice that the authors who pointed this out are the same who also proposed this dark matter direct detection experiment, which was mentioned yesterday. Good. So essentially this means that whatever you do, you will always have some kind of an ugly model of grand unification as long as you stick to four-dimensional. This tells you, okay, you could do like Francesco did in yesterday's talk, you go to extra dimensions. This is all fine, except for the little detail that gauge series in more than 4 dimensions are not renormalizable and therefore strictly speaking not predictive. So you can only make sense of these kind of theories if you have something, some UV completion, which allows you to make the theory in the end predictive. And as of now, there's only one theory which does that, which is known, allows you to do that, which gives you a UV completion of such higher dimensional edges, and this is string theory. In fact, string theory requires extra dimensions. It's not that you want string theory to be true, it's I want these extra dimensions just in order to solve the temperature. It's something which comes out from consistent simulation of string theory, some cancellations of some anomalies. It's of course celebrated Schwarz paper, but it just tells you that if you really believe in unification and go through all these arguments, it strongly suggests that in the end you will do something like string modeling. Because then you have a handle to solve the double tuple splitting, probably in the very same way as Francesco did yesterday, but with a UV completion. And this, of course, then raises the question, so what is the status of neutrino physics in the context of string modeling? So what can string theorists say of how neutrinos work? And let me just start with a very simple excuse. I mean, physicists have been playing with strings for a long time, so I can also do that. Yeah? So we are going to play with strings now. It's of course not really clear or well defined what string theory really is. So there are many different attitudes towards that. We know that there is this so-called mysterious M theory, which may or may not be some ultimate theory. It has all sorts of perturbative limits, which are the known string theories, they come in different versions, or some 11Ds for gravity. And nobody really knows what this M in M theory stands for. It could be Marmot, or it could be Mexico, we really don't know. Anyway, but there is a mysterious theory which we don't know too well, but we know at least these perturbative limits, and we can work with any of those, and can try or can hope to find something like the standard model somewhere there. So, of course, to make a working assumption that we say, okay, the standard model can be, let's say, found close to this corner. And we take this version and do some perturbation theory here, and it may or may not work. And of course, different people have tried different things here. And I'm going to mainly focus on this version, and this is simply again because of group theory, because this one comes automatically with some 8 which contains the SO10 and naturally the standard model generations. If you have, and there is a lot of work on string theory, even with black holes and whatever, and it's really has been tested theoretically in many, many ways, and it seems to provide us with a consistent theory of quantum gravity. What it means is it really contains gauge interactions. Local gauge symmetries are part of string models, and gravity, but without any problem of a non-randomizable theory. So there are certain divergences which happen in ordinary quantum field theory, which will tell you that you need an infinite number of counter terms, meaning that the theory does not become predictive, but in string theory it doesn't happen. So in a certain way, these divergences are effectively cut off by string length. And of course, I mean, this raises the hope that this framework will ultimately allow us to have a unified description of nature. It's not clear whether this really happens, and we only understand this thing partly, but so far it doesn't look bad. And one thing which is in a certain way intriguing in this context is that string theory always required extra dimensions. I mean, previously I wanted to argue that somehow if we want to keep the scheme of quantum unification alive, we have to buy extra dimensions. But string theorists are fine with it, they even require it. So when they even make a prediction on the number of space dimensions, it should be 10. Of course, And as I stand here, I see already 3 spatial dimensions. There's some time flowing. How much time do I have? 12 minutes. So there's some time going on, which is less and less. Anyway, so, but there are, of course, I see only 3 spatial dimensions part of the time. This tells us that 6 dimensions have to be invisible, and the best known way to make dimensions invisible is to compactify. To just say these dimensions are curled up on a very tiny space, shape, which we cannot see or resolve with our current colliders, and therefore they are effectively invisible to our eye or to our detectors. The game of string model building can be compared at some level to the game of constructing a violin. You see, if you have a violin, you want to construct it in such a way that if you excite the strings here, this gives you the right sounds. And of course, there's an art of violin construction, but if you're a master, then you have to create a violin which produces the right sounds. The excitations of these strings have certain very nice properties. And string model building is in a certain way very similar. You compactify the strings in some compact space, some compact internal manifold, but you have to do it in such a way that the excitations, or the massive excitations here, are precisely carry the standard model of the standard model particles. So in this point of view, these standard model particles are just some basic massless excitations of some crazy compact space. Clearly, I mean, this cannot be depicted in such a simple fashion as this one, but the analogy is like this. You really have to build up some compact space such that the excitations are those give us the particles of the standard model, maybe plus some extra stuff for dark matter or whatever. So that's what you want to do. And of course, there's a mathematical framework which you can go through. Saul wrote this very nice program, the Orbit folder, which does many of these steps automatically. You just now press a button and give some data on how this shape should look like. And Saul will tell you what are the particles, what are the massless particles which pop out. And if you do everything right, you get something like this. Of course, I mean, I have not the time to tell you how this works in details. It's not that trivial, but at least you can do it. There are many ways, of course. You can compactify this with test rings. There are the heterodic orbitals, there are Saul is world expert. There are the so-called intersecting E-plane models. There are the so-called smooth Calabi-Yau compactifications, which are supergravity models. There is a more modern development, which is F-theory, and so on and so forth. And of course, you probably also have heard of the big excitement about the swampland discussion. So people try now to figure out means or features of theories that cannot be derived from strings. So there's now some excitement of some idea to find certain things. If you would find this in nature, then you would be able to disprove things. To which extent you can trust all these statements which are made in the literature, I cannot tell. At least there's this discussion. So among all these, only the first two have some very old-fashioned string, honestly not string compactification. The last one can be related to them, and the third one is a supergravity construction. Anyway, I'm going to discuss here the heterodic orbitals. People have tried to find something like the standard model, meaning that you have something which gives you at the low energy excitations which look like the standard model. You have something where some string vibrates like a top quark, another one like a miniature, and there are many of those models. None of them is really perfect, absolutely not. I'm not claiming that anyone has found the standard model in strings so far. I don't think that is the case. But you can at least qualitatively reproduce the standard model. And the attitude which I'm going to adopt in the subsequent talk is just to say, okay, And nobody really has found the standard model for many reasons, also because we simply cannot compute all the interactions to the great detail they are measured. So this is, even if you have something which looks awfully like the standard model, we never really claim it is. But nevertheless, one can draw certain conclusions or learn certain lessons from these constructions, and they are, of course, conclusions which also allow us to understand the nature of neutrinos. So we can have a well-defined question. We could ask how many writing neutrinos are there in a given string construction. You can work that out. And Saul has produced maybe one of the largest sets of standard model mathematics. If you want more details, go ask him about the orbifolder, which is a very convenient program which does it for you, so you don't have to go through all the maths. And in a certain way, this small corner of the string landscape has more or less completely understood in the fact that we understand which orbifold geometries are possible. There are many, and up before 2013, over 80% of the possible geometries were not known to the literature, but now there's a complete classification. I started out the whole discussion, this also brings me towards the end, with a discussion of scales. In string theory, of course, you may ask, how do all these scales pop up? How many scales do I have in string theory? In string theory, there's of course only one scale, which is somehow the string tension or string length or whatever. And everything else will be derived from that. So Newton's constant derives from it, and also the gauge couples derives from that. And if you do the very, very naive thing, derive a scale from the string tension, and compared to the naive scale of grand unification, then you see two things. First of all, they are suspiciously close. So a priori, they are not supposed to have anything to do with each other, but they coincide within a factor of 40 or so. So this is one thing which people find promising, but of course there's also this factor of 40 discrepancy, which is a more transactive model. There's a long literature on this, there's some discrepancy, which you can solve by going to so-called anisotropic string compactification, to M-theory limit and so on and so forth. And the very last point, that will be the starting point of the next lecture, is just I certainly give you another perspective of what Francesco already did yesterday, namely to give you one specific example of compound dimension. There are many things which you have to be careful with. One of them is, if you would say, well, this looks very nice, looks like a donut, I take my compact dimensions to look like this. Very tasty and nice donut. Turns out that this doesn't work. And this doesn't work for reasons that have to do with Lorentz solution. If you live in higher dimensions, the spinor representations are larger than in 4 dimensions. In particular, you cannot have 4-dimensional Weyl spinors if you have such a very simple compactification. You get always non-chiral theories. So whenever you have 5, 6, whatever dimensions, and you don't do anything special, you end up with spinor representations which do not at all resemble to what we observe in the standard model. And one way to get rid of this is the so-called orbifolding. Orbifolding kicks out sort of 50% of the chiralities and produces a chiral spectrum. So what is orbifolding? Orbifolding just means you divide out a symmetry. So here in this, I can represent this torus by this object, was just saying, if I run out here, come back here, run out here, come back here. But now you see this thingy has some symmetries. These symmetries actually will be important for the flavor symmetries, which already have been discussed and will be discussed again. So one of the symmetries which I could work out is here rotation by 180 degrees. You see, if I rotate this thingy by 180 degrees, it's the same. But if I do this, this means somehow I identify this point with this point. What it means is 50% of my points get redundant, because this point is already this point, so I have to kick it out. I have this just a fundamental domain, which is 50% of the original space. Now, there's 4 special points which are special, which do not move under this rotation. So obviously this point doesn't move. This point gets mapped here, but we live on a torus that such that this point coincides with this point, so this point is fixed, and so on here. Even more, one can visualize the emerging geometry by just realizing that if I run out here, I come back here. If I run out here, I come back there. So I can glue these the fundamental domain. I can fold it to some object. I can glue these edges together. This is part of the reason why it's an orbifold, so you can fold it. And what happens, what emerges from this, is some space-time which looks like a tasty ravioli. So this is what you get at the end. And this is something which in a certain way has discussed yesterday. But these are the geometries which I'm going to base the first part of my tomorrow's talk on. And you will see that these points, these special points, have very important implications on important role. They will carry the standard model representations. So there will be models in which if the electron lives here, also the up quark lives here. You also see that somehow you see these points look already similar. You could in a certain way transform them into each other. This of course will then give us more light on the original flavor symmetries. Because you see, I mean, this has already been discussed yesterday. We have symmetries which relate to points. And this can play the role of flavor symmetries. But I think this picture is actually a good point to stop it of discussions.
Thank you. Thank you very much. Thank you for this very nice lecture. So we have time for questions. Yes.
Bertrand Russell, in his book on scientific perspective, tells that in modern science was already at the time of Russell, that you let the theorists, the ingenuity of the theorists, to invent possible behaviors of nature. And it corresponds to experiments to decide which of these models is really the one of nature. I mean that.
Yes, let me just give you a famous example. Pauli, when he introduced neutrino, apologized for the fact that we never discovered an experimentalist proved him wrong. So this is one example. I mean, yes, it's true that ultimately we want to test it, and of course it takes very big efforts and experiments to
But
communication between fields.
Probably I should explain myself why I started with this comment. I think I have the feeling that it's necessary to find paths in order to connect, ways in order to connect with possible experiments that, you see, that really support the general idea. Because we tend to the 7 different standard models or so, then it looks difficult really to work. What are the consequences which are possible at the low energies?
What are you suggesting, to build a bottom-up model which is somehow has an issue with consistency?
You see, in the string idea there is a fundamental idea, which is that there is a fundamental length.
Yes.
Okay? And then the interactions at the end are not local. Local.
Yes, in some sense local, but in some sense they call it not local. Okay?
No, local only when you have defective theory. But you see, in the word of the string there is the fundamental length and these are not local. That means that automatically, this is my feeling, the CPT theorem should be broken.
No.
You see, this is a kind of argument that I used to with my string theories friends. Let's put it like that. I think one should take a general attitude that extract the main points and see that, you see, the idea of a local field theory is present in something as important as the CPT theory.
I know this.
And you see, there are systems these days in which the CPT symmetry is being tested at the level of only 1-2 orders of magnitude below the Planck scale. Why? One say because you say, okay, the Planck scale is one energy, and the other, and we are at very low energies compared to that. But yeah, but in the quantum world, there is the energy denominator that I call. That means when you have a very small effect, but you have almost degeneracy of the system, then you enhance the effect by many orders of magnitude.
This is so true, yes.
And this is what happens with the almost degeneracy of the K0, K0 bar system, the
Sure.
K1, K0. And in these systems, they put on limits these days on CPT violation, which are at the level of 1-2 orders of magnitude below the Planck scale.
Yeah,
I think this is a possible path in order to test the main idea, not one of 10 to the 7 models, okay? But the main idea that there is a fundamental there. I would like to see, you see, work in that direction, to see what are, you see, the manifestations.
the problem is that, I mean, it's not true that string 3 would unequivocally predict CPD violation at the level you are talking. That simply it doesn't. Yeah? So you can certainly build up models which do. But you have to work very hard for that. So
Probably you have to work very hard.
But why would I work hard for a model which has an incredibly large, my strength needs in its FATC a very large amount of CPT violation. Maybe I can succeed to find such a model, then the experiments go and find the limit and it's not there, then okay, this model is wrong. Okay.
Yeah.
Why would one do that?
Okay, I don't have the recipe, but I think, you see, the community of the string theorists, I think that they have the means in order to attack this question.
No,
Because
they have,
I
but
think,
they have, but
I think this is, you see, this is one of the panels, if you want, to connect this world with the world of the behavior of nature. Through this kind of general point that there is a fundamental length, which I do believe.
Yes, but you
that there is
cannot
a fundamental
prove this.
length in nature. I don't believe that nature follows mathematical points in the interaction. You see, but one has to connect with this. You see.
So do you want to reply or we have another question?
I just maybe very short thing. I think
Okay, we
does
are
not.
not
No, please.
It's a comment, it's not a question.
Okay, do you want to?
Yeah, no, come.
Please.
So I think everyone is interested in connecting Pepe, and I think I think he just answered. I mean, it's nice what you're saying that this might be a tunnel and so on and so forth, but he just said that string theory does not unequivocally give you CPT violation. So that shows that it's not the tunnel that you're looking for.
I mean,
Unless you can prove that having this length scale immediately implies CPT violation for anything, for every string theory, which I bet you can't.
no, you can prove it
Right.
in the cases. Maybe can I give another example? People were some 20 years back, they were really excited about the idea of extra dimensions. After you realized they could be there and could be tested. Yeah? And it's a very exciting thing. But we have now not found any extra dimensions. Simply because in string models they can be large, but they can also be not large. So, of course, it's very exciting to go in space, but it's not necessarily clear that this gives you a unique answer. Just see, okay, we don't now have certain constraints on Newton's law at certain distances, it got much more precisely. It's an exciting experiment, I fully agree with that. But there is no such a probe. You have just something which you have to find and you prove or disprove string theory. I mean, this is the swamp-like discussion, but it's very controversial. They try to find something which certainly, if you have this, then the string theory has to be wrong, but there's a huge controversy, which I cannot add much to.
More questions, yes.
So this is, I don't know this was a little for me. So when you classify the standard like models, these 10 to the 7, are they standard model like in the gauge group and in the major content,
No,
or
they-
just in the gauge group?
No. They have the precise standard model gauge group. They have the precise chiral spectrum of the standard model, and you can show that you can get rid of everything which you don't like. They can be arbitrarily heavy. To show how heavy they are, you have to compute the couplings, which we have not done. But no, they have precisely the standard model gauge matter content, the precise gauge group, no obnoxious extra thingy which happens on the standard model.
So straight from one compartment.
Huh?
Straight from one compartment.
Well, these are different gauge embeddings and partly different geometries. I mean, here I show a two-dimensional example because this projector only computes two dimensions. But if you see, if you have 6 dimensions, it becomes richer.
So what about like SM plus something?
Well, you have, of course, you start in this model with E8 cross E8. You can have remnants of E8 which are actually often very good because they give you some dynamical scale which allows you to play supersymmetries or scale or whatever. Yeah? So you can like this or not. Yeah? These models obviously differ in these hidden properties.
Yeah.
The only good thing is you cannot put them by hand. People in the bottom-up literature say, oh, you see, I want to have this hidden sector, they add this hidden sector here. It's absolutely impossible. You see what the hidden sector is, and you have to live with it, or take a different model, but you have certain things and there are certain constraints, of course. There are many things, and as a next lecture I will start counting neutrinos. You cannot add neutrinos to this. Either it's there or not. Either there are 2 or 50. But strings will tell you how many.
More questions? Okay. Well, maybe we're expecting for the second lecture. So, thank you very much, Michael. So now we come back at 3:30.
Thank you very much, Eduardo. Thanks to the organizers for inviting me. It is a real pleasure to be here. So, the plan of the talk is to discuss 4 different topics, and I won't have time to cover them all properly, so you got me when I'm done, okay, please. So first one is about anomalous magnetic moments of muon and electron. So who knows that there are 2 different anomalies related to that? Who knows that before I start speaking? Who already knew that? Okay. Okay. There are some people who already knew that. It's not trivial, okay?
People know one.
Yeah, people, I hope that they know one. But, so this is really last news. I will discuss these both different anomalies and if they are real or not. So second topic is Charles-Lepton flavor violation. So it's kind of common law that any observation here is new physics, but this was not fully clear, and we made some work to clarify that. And I will emphasize this, and in the end, it will be warranted again that any observation is new physics as we expected. Then semi-leptonic tau decays. So we started with Fermi theory, understanding nuclear beta decays, and so on. We can go further and link this to the standard model, but now we can go one step beyond and go to the standard model seeing itself as an effective field theory, that's SMEF. And in this way, they are useful to put constraints on really fundamental physics, right, at a very high level. And finally, I will say some words about Michel parameters in leptonic lepton decays. Michel parameters are a very systematic tool for putting constraints on completely general new physics in this very clean decay. So one usually would expect that only muons are placing really powerful constraints there, but sometimes, in some cases, also tau leptons are bringing something new in. Okay, so this is the plan. So then both anomalies are present here in A mu and in AE. So very small here is the definition, but that's just recalling you that we are looking to the magnetic moment of the charged lepton. This is proportional to the spin through the charge and the mass of the lepton times the gyromagnetic factor, okay, of the given lepton, this G here. So this is 2 as given by that equation, but due to quantum correction it departs from 2, and this is encoded in this anomalous magnetic moment here, so AL. AL at lowest order is just alpha over 2 pi as given by this diagram with the photon, only with the photon, and this is the famous Schwinger computation 70 years ago, okay? But now we can proceed further and include not only QED corrections, that of course do not need to be at lowest order, up to 5 loop in QED, it has been done here. Also we have electroweak corrections that you can just get putting a C instead of a photon here, but also through these W neutrino diagrams. And this is done at up to 2 loops and 3 loops, including on the leading block contribution, right, for electroweak. And then we have this kind of diagram. This kind of diagrams are given for any fermion, so you have vacuum polarization type of contributions, and evidently if you ampute here the fermion legs, you have a kind of vacuum polarization contribution with a given fermion. So it can be either a lepton or a quark. If it is a quark, then it is the hadronic vacuum polarization contribution that is really problematic theoretically. Then similarly, we have light by light type of contributions, where again you can have any given fermion here, but in the case this fermion is a quark, then it brings problem, and it is the hadronic light by light contribution. For the anomalous magnetic moment of the electron, very importantly, everything is just QED. Okay, so the rest is completely negligible. AE is just AE QED, and this is not the case for AE. Okay, I will be discussing this. So, until half a year ago, there was just one possible anomaly. So this anomaly was, of course, in the anomalous magnetic moment of the muon, where there was an excess between the experimental measured value and the standard model prediction of this size with these errors. So this is 3.7 sigma deviation. And you see the really remarkable level of precision that is obtained here, both in the measurement and in the theory prediction. But the picture has changed very recently. So there has been an experiment in Berkeley announcing a new ultra-precise measurement of alpha using interferometry techniques. And this was just published in Science Mag. And what they have done? So they were sending photons of very well-defined energies to the cesium atom, and they were measuring the kinetic energy of this atom, so this was giving access to this factor here. And then independently, they know very precisely the ratio of the mass of the atom over the mass of the electron and the Rydberg constant. Using this formula, you can, from the measurement done in Berkeley, they can just obtain alpha through this relation, okay? And you see, this is petrology. I mean, they are not using natural units. They are using here C and H. So this is like a different field of physics, but it's fundamental, okay? So knowing alpha from this measurement, AE is really a series in alpha, because I told you all this part is negligible for the case of the electron. So it's really a power series in alpha that is known theoretically up to alpha to the 5. Then you have the measurement, so knowing alpha, you can get AE at the desired precision. So this is the theory input for that. And let me show you what is the impact of this new measurement. So this was a previous very good measurement using rubidium atom. So you see what's the error there. This is a direct measurement of the gyromagnetic factor. Okay, here we are measuring alpha, here and here. Here we are measuring the gyromagnetic factor. And this was previously the most precise value. Okay? Now the situation has changed because of this new measurement, and this is the result of it. Let me emphasize that this is statistically dominated, so they can accumulate more data and reduce the error. So it's going to be even more important in the future. So then, what can you do once you know this A obtained from alpha? So from the Berkeley measurement, you input theory, and then you get A of alpha. you can compare this with the direct measurement of the gyromagnetic factor, if you wish, done at Harvard some years ago, so directly with this, okay? If you do that, then the difference is sizable, it's more than 2 sigma deviation. But the most important thing is not the deviation, it's that the sign differs with respect to the previous anomaly, okay? That was 3.7 sigma deviation in the muon, but you see that the experiment was larger than the theory prediction. Now it is the contrary. Now we see that the difference comes with the opposite sign, and it's somehow significant. Okay?
In the electron.
Yeah, in the electron case. So in the electron case, the sign of the anomaly is reversed. So yeah.
Is this using only the one data or the combined?
No, this value is obtained using just this measurement.
And if you combine all the measurements?
Well, you don't want to do that. You could maybe combine these two. But you don't want to do that because they are somehow independent. So because this is a measurement of the gyromagnetic ratio, and these two are measurements of alpha. Then from this point of view, you would like to compare measurements of the gyromagnetic ratio that are here with measurements of alpha that are here. Of course, they are related through theory, but you would like to compare these two independently. And when you do this, you can really observe an anomaly if it is there, because they are independent sources. And this is what is seen finally here. So this is this anomaly. Now, I mean, we are here for discussing possible new physics signatures. This is very bad news.
But I have a question. Yeah. The number that you have for the muon anomaly is still the same or not?
Yeah, the number for the muon anomaly can get updated only by the new input on alpha. But this is not making an effect on a mu.
It's not important?
No, it's not important. I will show you the uncertainties are hadronically
What was the point? That the muon anomaly appeared using alpha from electron anomaly.
Yeah.
Now you say, okay, I take alpha from something else.
Yes.
And you say the muon anomaly remains equal.
Yeah, I will show you that here. What is important are the hadronic uncertainties. Even if you shift alpha by this, it is not significant.
That means the difference is in the hadronic uncertainty.
Exactly.
Inside.
Exactly. That's it. Okay, so if we are looking for a natural explanation of this simultaneously, it's very hard because any new physics that you put there would tend to contribute with the same size to both A mu and AE. For instance, the Berkeley result rules out dark photon explanation of the A mu anomaly at the 99% confidence level. Let me show you this. So here in this plot, it is this dark photon, so it is logarithmic on both axes. And this is the dark photon mass with reference to GeV. And this is the dark photon coupling, it is epsilon squared. Then this band was providing a solution at 2 sigmas to the A mu problem, right? It was already in big tension with Babar direct searches for dark photons and also from data from Keon decays. Now this band that you can see here was a constraint coming from this measurement here. Okay? It was already important. But now it is much more important if we take into account the restriction coming from this measurement here. This is giving us this orange band here. So if you take everything into account, as I said, an explanation of the mu anomaly through dark photons is disfavored at 99% confidence level. Okay. Then you could say, okay, I don't believe A mu, can we explain AE? So since the sign is different, you could do this, for instance, with an axial. Okay? And this is the plot for axials. So for axials, again, this is the axial mass, now reference to MEV, again, logarithmic scale, and this is the coupling. And you see that everything that was explaining anything there is already ruled out. So it would be, I mean, you see here it's pi 0 to E plus E minus, eta to mu plus mu minus. This is the previous measurement from rubidium. So this is ruling basically all parameter space. There is a very tiny island of hope here, but I don't think this will survive very long. Okay. So any way you look at it, a simultaneous explanation of both anomalies is very difficult unless it is quite fine-tuned, or of course it violates lepton universality, but very dramatically. So I mean, I wouldn't believe that in principle. Okay, so my personal view, and this is I emphasize what I think of this, is that the anomaly on AE is not that significant and will be reduced with more precise measurement of GE. So the Harvard measurement, now there is really a very strong case for repeating it with improved precision. And once this is done, probably it will come closer, if it is a statistical fluctuation, it will become closer to the measurement of alpha, okay, with the cesium atom. Also, as I told you, the cesium measurement is statistically dominated, so with more data, they will have more precision. So that's what I think about AE. Now, about A mu, I don't think that currently we can say anything about new physics there. I think that there we are still limited by hadronic uncertainties, okay? And when we improve on that, we can look at this, searching for new physics, okay? That's my personal
So if that is the case, all the exclusion plots will change. Those.
Yeah, okay, so here, for instance, yeah, maybe the central value here is wrong, maybe the uncertainty value is wrong. Yeah.
This delta AE disappears.
Yeah, this,
Everything will change, right?
yeah, this is what is explaining you A mu. So if the hadronic uncertainties are badly evaluated, let's say, this can shift central value, this can shift the width of the value. In any case, I mean, it would need to be really strong shift so that it remains compatible with any of these for A mu. Then for AE is different because for AE, I mean, you see the change from here to here. So it may well be possible that with a new, more precise measurement of GE, it goes somewhere here. So that's what I believe it would happen. Let's see what data tell. Okay, so yeah, this is what I want, discussion. Okay, if I don't cover the material, it's fine. We can keep on discussing later. Okay, also from the studio. Okay, so yeah, this I already said. Now I said that AE was basically the QED contribution. Let me show you this really. So this is hadronic vacuum polarization. This is basically 2 times 10 to the minus 12. These are subleading contributions, and you see that they are pretty much smaller, and including light by light. So, to a good approximation, this gives us basically the ballpark of this contribution. Okay, 2 times 10 to the minus 12 for the hadronic part, okay, to AE. Now, what about the other contributions? Electroweak contributions is even much smaller, okay? And now you can see the complete thing. So this is QED plus hadronic plus electroweak. And you see here that the error is fully dominated by the uncertainty on alpha, and it is more than 2 orders of magnitude larger than this. So QED is the only important thing for the anomalous magnetic moment of the electron. Also, looking at the size of the electroweak contribution, I mean, it would be really astonishing that a new physics contribution can be of any big size, right? Because I mean, this is a natural measure for a contribution from larger scales, let's say. And this is incredibly smaller than the things that matter here. So it is QED, okay? And that's why I expect that with new measurements there will be no anomaly on this quantity. Also, you expect that the electron is less sensitive to new physics. So the overall picture is that with new, more precise measurement on cesium, they are acquiring more data. And they are statistically limited. And also, improved measurement over the Harvard's one on the geomagnetic factor, everything will be fine for AE, but with better precision. Okay. Now, what about A mu? So this is the time evolution of A mu, and then you have measurements in blue, final point in black, last cell point in green. So these are measurements, and theory predictions in red. So this talks basically 15 years ago. Obviously, in the last 15 years, there hasn't been any new experiment, so still the Brookhaven result is the current one, but we will have improvement very soon in the future. So FNAL will release in less than a year from now its first measurement with an accuracy comparable to the final FNAL measurement. and it will be improved by four times, improved in a couple of years. So we will have a very, very solid experimental measurement of amnion. Now on the theory side, there hasn't been great changes here, but now this is changing thanks to the mu-ng-2 theory initiative that is working towards a similar reduction on the theory error. Okay, I will give you some more details about that. Okay, so that's...
Before you move, you see, what you call the theory prediction of the vacuum polarization for the hadronic part depends on the experiment. The theoretical prediction depends on the experiment. And you see, I don't know at the end what happened with this history, but there was a discrepancy in the theoretical calculation depending whether you were using for the vacuum polarization through the dispersion relation and so on, the cross-section of the plus minus to hadron, or you see, what is the present situation in that? You see, because there is an uncertainty in the theory which is coming from using different experiments. Is it true?
Yes, it's true. So let me be very brief on that. Now lattice has entered into the game, and currently the most precise hadronic vacuum polarization contribution is still the one you can get from E plus E minus to hadrons experiment. But for the future, the most precise evaluation will be data plus lattice, because lattice can improve in some regions where you cannot measure that well. And this combined effort will lead to a really dramatic reduction of the error.
That means you are not using tau decays anymore.
Okay, so
only E plus E minus.
Yeah, basically yes, but not
particularly in your case, tau decays.
Yeah. In fact, there are at least two groups working on that. So on the lattice, it may seem unbelievable, but it's true. On the lattice, they are computing the isospin breaking corrections that you need to relate E plus E minus to hadrons to tau to hadron data.
Yeah.
This is done on the lattice, so it will be very important because to some extent the computation of these corrections are model dependent. So this will be a check. And we are also working on, on this chiral evaluation of this isospin breaking, trying to improve our previous evaluation by Chirigliano and collaborators, and also by Gabriel Genaro and collaborators. So this is being done, but it is just one of the ingredients. So others are coming into the.
So Pablo, one question: when you say calculations on the lattice, you mean at the physical point or extrapolations to the physical point?
No. Okay. I can give you more details about that later on. But for the
okay,
we will discuss later on. I have this thing, but I will need a lot of time to discuss.
Okay.
But they will be really useful. That's the short answer, because they are very good precisely at the regions where you cannot have really good data or control of the Monte Carlo radiative corrections if you use E plus minus data, or of the isospin breaking corrections if you use tau to hadron data. Okay, this is Mattia Bruno, maybe you.
Okay.
Yeah, yes.
On another remark you made that the corrections to tau decays is model dependent. Jägerlehner and Chaffron say it's not. They say it's an absolute prediction. So you disagree with them, or?
Okay. About this, I also need time, but I want to say something because here most of the community are misled. So I think it is very important to discuss this. Okay, so what Jägerlehner and Chaffron do is that they consider raw gamma mixing, and also omega is included in it. They included this thing. Okay, and then they say, okay, you need to take into account these effects. Then you not only have E plus E minus going to a photon and then hadron, but you may also have mixing of this photon with the error. And then they do in much the same way as you would do for the gamma C mixing or whatever in field theory at the electroweak scale. That's what they basically. But here you are dealing with particles that are clearly composite in the case of the rock. And they treat all this stuff as they were elementary particles. So this you can do. Okay, so just from this observation I would say that the result is not fully reliable. Okay? But doing this, let's say, correctly, so If you want to couple the gamma to the rho, maybe you also need a pion loop in between to say it in an easy way. To do this consistently, including all that, is really a nightmare. So, I mean, it is interesting, and I mean, maybe we will look at that at some point, some other people will do. But nobody has done that because it's very difficult to go beyond what Jägerlehner and Saffron have done. Okay? But I will take with a grain of salt the result because of this. They are proceeding as if the rho was an elementary particle, and this, for sure, is not granted. You may not have right results because of that. Okay. Okay. So I was somewhere here. So yeah. So here it's just to show you that here the errors are hadronic. Okay, in AMU. So this is the error on QED. It is pretty negligible. It is very small also on the electroweak part, and then we have for the hadronic part. So this 37 for hadronic vacuum polarization currently is not. I mean, in the PDG you will not find something smaller than 30. But in some published papers you will already find 27, 28 here. Okay, so it is this the direction in which we are moving. And once this is combined also with lattice, the dominant error will become the one in hadronic light by light. This would seem unbelievable some 10 years ago. Okay? So now the theory effort should focus here. Okay? Also because the error here is not widely accepted. Okay, so then what are the developments here? So on HVP.
Yeah, but this 37, okay, or in particular the 26. This is a theoretical error, which I put these always in brackets. You see? What is the meaning of the theoretical error? You compare different calculations and then you see what is not. The theoretical error is somewhat misleading. Mm-hmm. Do you agree with me?
Yeah, in fact.
You don't know whether it's 26. This is only. Okay. You cannot say, it's not like in the case of QED, that really you have a trend in this. These errors in the hadronic contribution come from comparison of different theoretical calculations, which for hadrons probably, okay, is somewhat misleading, is what I think.
Okay, yeah, so one of the, really, this brings me to the...
I think it's clear. Light by light will become an important contribution.
Yes. Yeah,
this is the conclusion.
Depending on who you ask, it will tell you that it's already dominating. But if not now, it will be in a couple of years from now. So your remark is really one of the motivations of this mu and G minus 2 theory initially. So the community wants to come up with numbers that are really solid. So numbers that come from comparisons, I mean, piece by piece, detailed things. So, I mean, doing some things on lattice, some doing things with experiments, some things with E plus E minus, tau data, so on HVP. On hadronic light by light, it is even more difficult because, contrary to HVP, in HVP there is really a well-defined, complete data-driven determination of HVP. Then, I mean, if you don't control well enough the Monte Carlo, the isospin correction is another issue. But in principle, it's data-driven. So you just improve your measurements and you improve your determination. But in hadronic light by light, it is not yet the case. So there has been a very, very strong effort, mainly driven by the Bern group, also the Mainz group, and on the lattice Connecticut mainly, so towards data-driven determination and lattice determination. Other analytic approaches are still being pursued, like large and seek, IPT, Dyson-Swinger equation, rational approximants. And then in these meetings, we really examine piece by piece, contribution by contribution, everything that comes into the game until some solid agreement on the error budget is reached. Okay, so I mean, and at least the aim is to go in the direction of solving the problem they're pointing at. Yeah, okay. It doesn't matter if I just cover one topic. Okay? I will have time also to cover the it really doesn't matter. You can look at it and we can discuss later. Okay, there was a problem here. No, not here. There wasn't a problem. Okay, so this is just some publicity, okay? I mean, it's just to show you that one can do things, and this is the things I have done. But for instance, James with Genaro have also contributed to this in a PLL 2003, something like that. In the hadronic vacuum polarization part, you know, the work by Gabriel, Genaro, other people, so I mean, just this is to show you the way we have been improving, no? So we did something together with Adolfo in his PhD. Now, in a more recent work in his postdoc, we have included first flavor breaking corrections to this result, and this is an improvement that you can do. In some way, it is controlled. Okay. Unfortunately, we have a theory systematic error that we cannot improve right now. It will improve in a future work, and we know how to do it, but we need time. Okay, and this is compared here to some other evaluations that you can find in the market. Okay, I know these are world leaders evaluations.
But this is only by zero intermediate.
Yeah, thank you. I forgot to say that.
Because I see in the left-hand side.
Yeah, no, you are right, and I forgot to say it. Okay, this is only pi zero. Pi zero is the most important contribution. Okay, we also have eta prime. For instance, you have contributed to the scalar contribution, others. I'm just focusing on the most important contribution because of lack of time, okay? But this gives you an idea of what's going on. So this will be appearing very soon, okay? It is a work in collaboration I've done with Kepa Mihai and Adnan Basir. And you see that this has very, very reduced error, and we believe it is controlled, okay? We will see what the people say and the experts and all that, but I mean, there's a direction for going further, okay? So, this was the first topic. Do you want to ask something else on the first topic before I move to the other ones? Students, I haven't had any questions from students. If not, I will ask any student that I will choose. Okay, so Charles Lepton flavor violation, Pepe will say more about that, okay? And everyone knows that any observation here is new physics, right? So I will show you that it's not the case. Okay? There was a particular situation, but this wasn't clear, and we clarified together with Gerardo, who is sitting in the back of the room. Okay, so Charles Lepton flavor violation is forbidden in the limit of massless neutrinos. Lepton flavor is conserved. This I know that Muchun already emphasized. So why this is small? Because neutrinos are running in the loop, so the partners of the Charles Lepton are those in the loops, and these are the neutrinos. And this brings you a very big suppression, because in addition to the J suppression, then you have ratios of neutrino masses over W masses squared. Okay? But the other ingredient is the Calibration.
You know that in the late 50s of the 20th century, before the two neutrino species, Feinberg calculated this contribution assuming a single neutrino. The branching ratio is 10 to the minus 4.
Yeah.
If you put only one neutrino,
Yeah.
the same for muons and electrons.
Yeah, this you recall in your lectures, and I think that Eduardo also uses to mention that in his courses. Yeah, but it's good that you recall this, because I forgot to put it, and it's interesting, especially for the students. If you have not understood
Really, the best,
ask them.
you see, it's the best demonstration, even better than the Brookhaven experiment.
No.
But that really you have to have two neutrinos.
Yeah, absolutely. No, this I fully agree. Okay, so what is the other important thing here? The KLM theorem. Okay, kinetically non-invertible. So this is telling you that you can have, it's not mathematically allowed, to have infrared divergences associated with intermediate final state particles. Okay, you cannot put the decaying particle mass to zero, because then you are left without decay. Okay, but the others, you in principle can put their masses to zero, but you cannot have any infrared divergence. Okay, this is mathematical theory. So there was a result in the market violating this, and this is why we were requested to perform this calculation to clarify the situation. Okay, so let's start with simple things. Mu 2 gamma. Mu 2 gamma, if you look at the branching ratio, you need to compare this diagram to this diagram. So then you count similar things. So we have this weak vertex here, this weak vertex here. This is the same as here. Okay. Then we have one W propagator. We have one W propagator. What is extra here? So this electromagnetic coupling, and then this other W propagator, and then the thing associated with the neutrinos, propagation and mixing, right? So just observing this, you know that you would have an extra factor of alpha, and also this part you know, okay? you don't know the factor of 3 over 32 pi. For this you need to do a computation, okay? But apart from that, you know everything. Just counting, just comparing. If you do that, you realize that the suppression of this is enormous at the level of 10 to the minus 50 something, okay? And a similar suppression has to arise in any other charge-lepton flyover vibrating process, okay? And that's what's in the literature. So C to L prime L is at this level, okay? This is a computation by Iana and collaborators, and now Gerardo is going for a postdoc with Iana. And this is Higgs to 2 different flavor leptons, and this is at the level of 10 to the minus 55 in this minimal extended standard model. And this is computation by Maria Jose Herrera and collaborators, okay? Then, I said, a similar suppression has to arise in any other charge-lepton flavor vibrating process. Is this the case or not? So the experimentalists, and I mean Atlas, Babar, Bell, and CMS, for years, for almost 20 years, they have been citing this result. This result is impossible. There should be no doubt about it. If you look at the matrix element, it has this form. Okay? So it depends directly on the log of scales. Now, if you look to Petkov, here we updated the input. Okay, if you look at Petkov times, you know really nothing about flavor mixing. So he was quoting values between 10 to the minus 30, 10 to the minus 40. But it was because he didn't know this precisely. If you just update his analytical results, you get 10 to the minus 50 something, as it should be, okay? So nothing strange about the result, but this result is impossible. And if you compare and take into account the KLM theorem, everything is clear. If you put the neutrino mass to 0, this gives an unphysical infrared divergence. If you put here the neutrino mass to 0, it goes smoothly to 0, as it must. Okay, so this computation is wrong. We were requested to prove it and discuss it and give an updated value of this.
You don't need to put the mass equal 0. Degenerate.
Yeah.
If you put degenerate, then it's 0.
Yeah, this is...
The point, this depends only on delta M's.
Yeah.
That means you know very well, because this is what you measure in neutrino oscillation.
Yes. At this time we know.
I mean, you don't need the absolute value of the mass.
Yeah. I wanted to make a connection with the KLM, but your remark is, of course...
It's only mass differences that matter.
Yes. And this you know from oscillation. Okay, so that was our duty, and this is what Gerardo did. So these are the diagrams that you get. It is very important that because of the Jim suppression, it is so effective that you really need to have two neutrino propagators. So two nearly massless propagators to somehow overcome it. That's what you do. So this is the only part that is important. Okay, so let me focus on this. And this, I mean, it's not easy to do, okay? But a number of different checks have been performed. So two different analytical evaluations, both with Feynman parameters and with Passarino-Bellman functions. Two different numerical computations, fully numerical with PAVE, that is better for numerical computation than Feynman parameterization. But also using what should be done here. Because what's the small scale in the problem? The small scale in the problem is the neutrino mass. So if you want to do this efficiently, the best way is to expand around m mu equals 0. If you do that, then your results are much simpler. The numerical evaluation is really trivial, and this wasn't done before. And this, when we did, we understood that the results in the numerical evaluation were right. Okay? And also, this is something that is interesting. So we have kept for the first time external momentum masses. If you do this changes the results at least by 1 order of magnitude. And you will tell me, okay, I mean, you are talking about 10 to the minus 53, 10 to the minus 54. Do you want to struggle because of this 1 order of magnitude? Of course not. I mean, this 1 order of magnitude is not important. But, in general, there are many computations that are done neglecting external momentum masses. So one needs to take a careful look at the literature to see if there is some process where this may become an issue. Okay? This we haven't done, but it's interesting to do this check. Okay, so here I'm just summarizing. So this is our result. This is Petkov's result with updated input, of course, and you see some 1 order of magnitude change in the mu to 3. And then the change can be larger, some factor of 50 maybe, depending on the channel for tau to lighter level. Okay? So if you consider some interesting physical process where you need to keep external momentum masses in computations involving boxes and things complicated like that, Gerardo is one man that can do that. Okay. Okay.
Okay. Your comments. Okay. I'm sorry that.
No. Please,
but
please,
this
please.
to me is a very important subject. Okay. Your comments refer to the decays to 3 leptons. Okay.
Yes.
Okay. This is the first thing.
Yes.
Not the mu E gamma or mu conversion. No. The decay to 3 leptons. Okay.
Yes.
When you have decays to 3 leptons, you see this process is delta L equals 0. But because there are, you see, the initial lepton and 3 leptons, if neutrinos are Majorana, the situation is different.
You are asking me about our next paper.
Oh.
If you want to go ahead, go ahead.
Okay. If you don't want to put me in the paper, then I may not go. Okay, now the comment is precisely that in this lepton, okay, this is something with Arcadi Santa Maria, my former student, we made in the, in what is the decade, the 90s, probably. I don't know.
For the C to ES bar? No, for the lepton.
No, for 3 leptons.
For the 3 leptons.
Because it's only for 3 leptons.
Yeah.
In the decay to 3 leptons, even if globally is delta L equals 0, okay, it's clear. You have that, you count leptonic number and so on, because you have the 2 vertices. You can have delta L equal to 2, delta L equal to 2, okay, for the globality. That means if neutrinos are Majorana, then one has to be careful with this kind of contribution.
Even without neutrinos.
You see, for Majorana neutrinos, you could have contribution in the intermediate state. You see, you go from lepton minus to lepton plus there through the Majorana neutrino. You see, in your diagrams. Yes. Okay, put a cross in between.
Yes. This will be the first paper for Gerardo and his post.
Yes, for a Majorana neutrino, really, you have a cross. That means you have an arrow from the left and an arrow from the, not from the left, at the end is from the right, okay? And then you have a mass insertion in that case. Because anyway you have mass insertion because of the gene mechanism.
Yeah, I hope that in any of the Spanish workshops, Gerardo will be explaining this and discussing it to you soon.
Yeah, because
so
this we have, because you see the thesis of Santa Maria was Majorana neutrino.
Yeah.
And then we are remarking this. You see, the people didn't realize that this process is different from mu E gamma or mu E conversion.
Some people...
Because they are for sure delta L equals 0. But this process can be delta L equal to 2, delta L equal to 2.
Yeah.
In one line and in the other line.
And in fact, let me tell you that the experimentalist that requested this analysis, he also thought about this. So some people are aware of this. And it's very important.
Yeah. The Majorana neutrinos could
Yeah. So it's also for the experimentalists a very big contribution. Okay, so I don't know how much time...
Anyway,
No. On the contrary, thank you.
I was announcing your...
Gerardo is very happy. So how much time do I have?
But look into this.
I mean, just to know, yeah.
Look into this paper with Arcadi.
Okay. Thank you. So now I will explain the idea, and if the idea is clear, then you can look at the result. So what's the idea? The idea is that once upon a time we look at the Fermi theory, and it was a first approach to charge current beta decays, charge current processes. Now this can be linked directly to the standard model, okay? And then you can understand things like this, no? Okay, the W is so heavy that since the momentum transfer of this process is very small, I can integrate it out, and then I reproduce a local effective interaction. And when I fit the possible coefficient, it turns out to be, to an excellent approximation, almost B minus A. Okay, so that's what everyone agrees. But we can go beyond that. Okay, and we can say, okay, let's look at this. What are we really doing? So we have the standard model, but we have this thing. Then we are applying the Fermi theory below the momentum transfer of the process. That is, for instance, much smaller than heavy coordinates, for instance. Okay. But we can go further in this spirit. So then we have the standard model, so this guy, we have it below the electroweak breaking scale. Okay. But we are of course interested in the physics that lies above some given new physics scale lambda that may be, according to current data, some TVs or higher. Okay. So we want to look at these DSMs here. then we just need to do the same thing that we did with the Fermi theory. So now we look at this guy as an effective theory. So this is dimension 4, and we keep on including higher dimensional operators with the standard model field. Okay? And this will be suppressed by some new physics scale lambda. So in this way, you can make the analysis of very low energy process, and with this system matching procedure, go and learn things about the fundamental field. This is what is done in SMEF, okay? Standard model effective field theory. And then this I apply in a couple of interesting processes. So tau lepton decays, and also leptonic lepton decay. I go a bit quickly on that. So just the result. So in this paper, together with Stella, that is Stella, is somebody here. Okay, so okay, so in this paper, we noted for the first time that semi-leptonic tau decays were important for this enterprise. Okay, and we obtained a very good limit for epsilon s. In this paper now with Alex, who is there, okay. With Alex, we have extended this analysis to 2 pi on tau decays, and in this case we are very sensitive to epsilon. Then Chirigliano's group has proceeded in this direction, and they have included our, let's say, our decays. Then they have added inclusive analysis, 1 pi on tau decay, impact on A mu by pi. So this is really the relation between using tau data and E plus E minus data. This can be affected by new physics because the new physics will be on the tau side, but not on the E plus E minus side. So it is very, very, very smart to do this. And then these are the limits that they get. Okay, I don't go through the details very much. I just go here. Let me mention that Aurora is one of the people that have contributed to this thing. Okay, so you can keep on discussing with her about that. But just the very short message. Okay, so these are our limits. You see, let's say 5 10 to the minus 3 for epsilon s, and here 1 or 2 times 10 to the minus 3. These compare very, very well to the best limits that you can get with other processes that were traditionally believed to be the best ones here. So radiative parallel decay and nuclear beta decay. Okay, so we really, I mean, here this is even a 0.9 sigma, if you wish, tiny hint for new physics. No? And this is not achieved in any other of these searches. So I mean, it is interesting to go on in this enterprise with tau decays. Okay, that's the main message. So here, let me finish with leptonic lepton decays, or not only muons matter. Okay, so very shortly, what are Michel parameters? You took the double differential decay width of a lepton into a given lepton and the corresponding neutrinos, and then this is double differential in the energy of the daughter lepton, okay, this variable x, and also in the angle between the polarization of the parent lepton and the momentum of the daughter lepton. Okay, so this is the more general contribution independently of the new physics that is there. Okay, so it depends on 4 Michel parameters if you are not measuring the daughter lepton polarization. Otherwise, there are 5 additional parameters. Okay, but for this simple case, only 4 parameters. So this is the usually called Michel parameter, but all of them can be called Michel parameters. They have very, very definite predictions in the standard model. And then, when you compare to data, I mean, it is in remarkable agreement with the standard model. So, seen from the other side, it places very, very stringent constraints on new physics. Okay. Then I am highlighting here one single contribution where tau decays are better than muon decays. Okay, there are others, but in the simplest decays, only here. And why here taus are better than muons? It is very easy to understand. Did I do something wrong? No. It is very easy to understand because if you look at the definition you need to make in the Fermi-like coupling, the theory in presence of general interactions, it is sensitive to eta, to one of the Michel parameters. But it is sensitive in a very particular way because it depends on this mass ratio. And this mass ratio is maximal when you take muon and tau. And that is why you can set the best limits here from tau decays and not from muon decays, despite the fact that muon decays are the ones measured with the best precision. Okay? There are other places where taus can play a role, and these come in through radiative decays. Okay? For radiative decays, again, taus are better, and then this is a measurement that was done for this decay. And for this decay, I wanted to mention that this is being done by Bell now, Bell 1 still, and this is using the formalism, the Michel parameter formalism, I mean, it is more complicated because this decay is more complicated than the previous one, but the idea is the same. Using this formalism of Michel parameters that we developed in this paper with Alain and Gabriel, okay? And if I can mention this to you, Denis Epifanov, who is our contact there, has found a very strong dependence enhanced by a similar type of argument in this particular channel. So there will be at least one Michel parameter where the best determination you can achieve is through these processes here. So no one could have told this before. Okay, it's interesting. Okay, so with this I come to the end. I really make it to the end. So what is the summary? Okay, so there seem to be a couple of anomalies here. I don't believe there is any anomaly here. Okay, and here I can know because hadronic uncertainties are still too big. Okay. Here Charles-Lepton flavor violation really, as anyone thought previously, any observation is new physics. If somebody tells you the contrary, this person is wrong. Okay. Then semi-leptonic tau decays, these are very useful for the big picture. Okay, going from very, very low energies to stringent tests of the field theory above some TEs. Okay, in a really, really complete, well-defined way. And finally, lepton decays are really the cleanest thing. Okay, and there you would think that only muons are giving you the strongest constraints, and it is not true. There are some particular Michel-like parameters that are best determined in tau decays, and this is going on. Okay, so since this workshop has this title, I thought I could finish with this sentence, and you can argue about that, discuss, so you disagree, whatever. But I thought I could write this here. Looking for new physics, some things you can't look at it just with leptons, but for some new physics that you can look at this only with leptons, this is clean, so go for it. Thank you.
Questions? Yes. I mean, the extraction of alpha from the Rydberg constant. I mean, the theory there must be also horribly complicated. I mean, you said that the uncertainty is dominated by statistics, but I mean, shouldn't there be more scrutiny before we blame it, I mean, if at all, at the AE? I mean, I can imagine that there's theory issues, or new physics could maybe also affect the Rydberg constant. And it's a real anomaly.
Yeah. I don't think I can agree more than I do. I will tell you some things about that. So, in the Tau Lepton workshop, all this was presented by Bill Marciano, and after the talks, I personally asked him about that, and I was not the only one asking him about that. He told me that as far as he knows, and I have read this, I couldn't find any theory reference telling how radiative corrections are already accounted for here. I imagine that some parameters are already defined taking into account this correction, but I cannot read it from the text. Okay. And I asked him, and he wasn't aware the precise way this is being done. So it is absolutely interesting that someone answers this question very precisely, because it may well be what you are saying, but I don't know.
More questions?
Yeah, in fact, this point, perhaps I can make a comment. This question is exactly the same as in the old times, in which the alpha value was taken from the Josephson method. Mm-hmm. And again was the question why the simple expression is true at the level that really we are testing. Okay, why not there are radiative corrections to the Josephson method, and now can be applied here. In that case, the answer was no. The answer is that really all of them corresponded to redefine the parameters of the relation. That means this is a relation which remains true to higher orders once you redefine what are the masses and what is the different quantities that appear in the condition. But it's important. It's important.
Yes,
this question. It's very important.
It's utmost important.
More questions or comments? If not, let's time out.
Sí, sí, no, hablemos.
And we have 30 minutes for coffee break. In concha break. ¿No? ¿Cuándo concha break?
Y los experimentales ahí no tienen ni un paper, de preguntar.
Okay. So in no.
Yo creo que no.
Es algo que he venido a recuperar, me interesaba. No, después de venir, no, me acaba de responder un referí.
Entonces, o sea, esto debe ser lo mismo, pero no está escrito. O sea, yo me imagino que lo han hecho bien todo, pero no está escrito. Y Marciano, que es un súper experto, le preguntamos varios de eso y yo no lo sabía. Dice, no, yo no sé eso. Hay que buscar a ver dónde está. Si está bien, pero si es importante. Si es una maravilla,
But in principle, it could be trouble.
Eduardo, ¿para allá?
A mí de verdad no es que me preguntan, no las tengo. No. So I don't know if it is going to be a problem. I don't know if you know, but they gave me ciencia básica. I got the grant, but still I haven't signed anything. I don't have anything yet. Just So I should ask that to. Right? I think it could be a problem, right?
That could be a problem. And then better somebody else.
Yeah.
So you got very high felicidades. Good, very good. Yeah.
So this was a very good year. I got infrastructure in my lab, so I bought a lot of that equipment, and now this one.
Excellent. But yeah, that may be because only one you're supposed
Yes, you're supposed to only be
within ciencia básica.
Yeah. Let me talk to Adela, right?
Yes. So, but who could do it? And would have to be Saul, or
Renata.
Okay, let me talk.
Yeah. And yes, let's go at 6, right?
Yeah.
For the check.
But
Or
maybe we sneak out at 5 and
Okay.
Yeah. Do you have? What does he need? A passport?
Just passport, and that's it. That's your
passport.
Mark Chen.
I have to fly Saturday morning to
9:10. To get to the airport Saturday morning.
At what time do you want?
9:10.
9:10.
5 days ago.
9:10, and so you should be there like at 7:30, right? Or less. 7:30, right? If the flight leaves at 9:10, you should be there like 7:30? Yeah. So
maybe
that means that
maybe
7.
Shoot for 7.
Yeah, then that means that at 6:15, 6:15, 6.
45 minutes.
Yeah, on
I mean,
Saturday
at that
morning.
time, it should not be traffic.
Yeah. And even if there's traffic, 1 hour is, I think, we need
So if you
traffic.
leave at 6, I think you should be absolutely safe, or even if you.
Okay, what's the airport like?
Which airline are you?
American Airlines.
That's Terminal 1, right?
I don't know. I can find it.
Should be Terminal 1. It's, well, so you need to know the terminal, which almost certainly is Terminal 1, so you tell that the taxi driver. He should be able to already leave you at the correct part of the curb, and then it's pretty much obvious.
There's a passport control and then security, I guess.
There is first, you check in, and where is that? Passport control. There is no passport control.
American Airlines, it is Terminal 1. Yes. Yes, American Airlines, and it is, yeah. It is definitely Terminal 1 here.
There is no
counters.
extra immigration thing going.
Yeah.
For us it is. For me as a foreigner resident here, I always have to go through the immigration people when I leave. But you don't have to do it.
Yes.
You only need that card that you probably have from coming in. That you have to show them. Okay.
I'll be outside and then we will just go at 5.
Okay, good.
Yeah, I guess the card they have, on the plane they give you a card and then I went to this machine, they gave me this stupid things and that's.
Oh, that was from a machine now?
Yeah, they had a machine, I
Okay.
put my hand on it and all that.
Ah, okay, that is new. I didn't know that. Yeah, looks good. I guess that's it.
And I had this card, they said if you lose it, it's the end of the world.
Well-
I took the card and threw it away and gave me this one. I hope,
No, I think it's.
I hope they knew what they were doing. I don't know, these guys.
And I think all what happens is you have to
Do it to
pay a
pay.
fine of
Yeah, they're the ones you have to
$20
pay.
or $30 or something. It's not.
I heard it also takes, it slows you down.
Well, yeah, sure.
And time, yeah.
Slows you
Which
down.
is not good, but yeah.
Yes.
So money and time, yeah.
I hope that's what they want. I hope the people I meet there know about the new system.
So what was your question about the writer constant?
Well, I mean, this is like precision of